All right, it looks like we're live now. Just a quick update. So one of the major milestones I was trying to reach in this class was to get up to lecture 10 and the first 5 problem sets. I sort of did that. I did watch up to the 10 lectures. In terms of the problem sets, I finished most of the first 5 problem sets. There were a couple problems I didn't work on because I needed to have some software installed that I didn't have installed on my computer. And there was, I think, one problem I didn't work on because there was an hour-long demonstration video to watch about it. There was also 2 problems in the last problem set I didn't work on because I didn't feel comfortable enough with some of the ideas. So there's still some material left from those problem sets I didn't finish. What I'm going to try to do now, though, is switch gears and focus on the the next set of lectures. So I did it kind of in an uneven batch because I did it splitting evenly on the problem sets. So there were 5 problem sets and then 5 problem sets. However, there were only 10 lectures, and now there's going to be 14 lectures to watch in this series. So my hope is that starting now Tuesday afternoon, if I can keep up the pace I was keeping at roughly, I should be able to finish by the end of the week all the lectures. Once I'm done all the lectures, then it's just switching just to practice. So I can just focus on just doing the work and doing the practice. You know what? I'm getting a lot of light bouncing up here from the bottom, so I'm just going to adjust my window. Just give me 1 second here. All right. That should make things a little bit better. Yeah, not quite as much glare. Unfortunately, this kind of lines up right with my face, this light from out from the blinds. But yeah, so I'm going to be working on the lectures today. So there's not going to be probably too much to see. One thing I did note from the previous set of lectures I was doing is that there were 2 lectures, lecture 8 and lecture 9, that I went through, but I didn't feel like I understood why everything was being done. So that was the brute force method for solving the simple harmonic oscillator, and then also the operator method. And I was a little bit confused as to why we were doing certain things and what was the motivation behind making certain calculations. And although I did kind of understand the result, I was, it just wasn't as crystal clear. So I actually went back and did those in quite some detail with the Feynman technique this morning and yesterday. And what that kind of has shown me, at least for this particular class, is because the difficulty is high, I don't think I want to push through a lecture if I feel like there was anything that wasn't clear to me in the actual lecture. Not to say that that's ever a good thing, but I have done classes for other classes, for instance, in physics, for MIT classes, where the derivation was there to show you why X is true or why Y is true, but then you didn't really have to have it mastered so much for actually doing a lot of the problems. You just had to know what the outcome was. So I remember, for instance, we did this whole derivation for the simple harmonic oscillator, in that case for the pendulum, and there was a lot of little details about, well, we're using small angle approximations and this kind of thing and this calculus and the like. And I remember watching that in that class, and it went over my head a little bit at that time, but it didn't matter so much because we weren't actually deriving it later. It was mostly just for understanding it. But for this class, I'm feeling like because the problem sets are harder, because I'm finding things are weaker, I just don't want to let anything fall through the sieve, so to speak. And I'm going to be a little bit more cautious. So what you might see me do is I'm going to watch the lectures a little bit more quickly. And then if there's something I don't understand, or if there's something that is going over my head, what I'm going to do is just either pause it and try to recap or figure out what's happening. If they're deriving things, I might try to even jump ahead a little bit. I'll see how much I want to do that. The jumping ahead sometimes is just bogs things down. But definitely on the understanding, I'm going to try to understand things better the first time through the lecture, because rewatching a whole lecture is not ideal from a perspective. And as I mentioned, normally my Feynman techniques are a couple pages. This was 12 pages. So it indicated that there was a lot of stuff that I didn't quite understand when it was happening. And so I want to avoid doing that. And I mean, part of that is also I'm doing it on camera here, so I'm still getting used to that. So as always, if anyone has any questions or things that they would like to ask me, you can just ask. I don't promise I will respond to things promptly, but I do try to respond to things when I work on it. And I also reply to emails. So if for some reason, you asked a question, I didn't see it in the chat, and then you wanted me to answer it, you can send me an email too. So let's go forward with lecture number, share this here. Lecture number 11 right now. Where are we here?
The following content.
I'm just gonna always scale it down for me here.
And is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today is going to be our last pass at bound states. So starting next week, or actually starting next lecture, we're going to look at scattering. Scattering is going to be great, but we need to close out bound states. So today's topic is finding potential well. We sort of sketched this when we looked at qualitative structure of wave functions of energy eigenstates, but we're going to solve the system today. So, good. So the system we're interested in is going to be, well, the system we're interested in is going to be a system with a finding depth and a finding width, and I'll go into detail and give you parameters in a bit. But first I want to just think about how do we find energy eigenfunctions of a potential of this form, V of x, which is piecewise constant. So first off, is this a terribly realistic potential? Will you ever in the real world find a system that has a potential which is piecewise constant? Probably not. It's discontinuous, right? So it's rather unphysical, but it's a very useful toy model. So for example, if you take a couple of capacitor plates, then you can induce a situation where the electric field is non-zero in between the capacitor plates and zero outside of the capacitor plates. Okay. So at a superficial level, this looks discontinuous. It looks like the electric field is, but actually, the microscopically there are a bunch of charges and everything is nice and continuous except for the behavior right at the charges. So, but it's reasonable to model this as a step function for an electric field. So this is going to be an idealization, but it's going to be a very useful idealization, the constant potential. Okay. So instead of what are we trying to do? We want to find the energy eigenstates for this because we want to study the time evolution, and the easiest way to solve the Schrödinger equation, the time evolution equation, is to expand the energy eigenstates. So the equation we want to solve is energy eigenvalue times phi e x equal to minus 8 bar squared 1 to 1 phi e plus v max x.
Okay, so this is just a recap of the same function we've been working with before, assuming the eigenfunction to m.
And I'm going to put it in form we've been using for e of x is equal to 2m on 8 bar squared v of x minus e. Okay, so this is the form that I'm going to use in
2m over h bar. Does this follow here? Well, we subtract this. So let's say we subtract the voltage here plus this, divide by all this. Why is there not a psi theta there?
To solve for the energy equation. E is some constant. Do you expect the allowed energies to be arbitrary? No, they should be discrete. Yeah, exactly. So we expect that there should be discrete lowest energy state, some number of bound states, and then eventually, if the energy is greater.
Why is there no theta here? Because if I move
continuous, any energy will be allowed above the potential. So we'll have a continuum of states above the potential, and we'll have a discrete set of bound states. Probably it's reasonable to expect some finite number of bound states just by intuition from the finite well, from the infinite well. So we expect a finite number of discrete energies, and then a continuous set of energies above zero. So if this is the asymptotic value of potential is zero. Okay. And this is intuition gained from our study of qualitative structure of energy. So we are going to talk today about bound states, and in recitation leaders should discuss the continuum above zero energy. Okay. So to solve for the actual energy eigenfunctions and the energy eigenvalues, what we need to do is we need to solve this equation subject to some boundary conditions, and the boundary conditions we're going to want to solve are going to be finite, so it's normalizable infinity. The solution should be vanishing far away, and the wave function should be everywhere smooth. Well, at least it should be continuous. So let's talk about what exactly boundary conditions we want to impose. And so, in particular, we're going to want to solve the potential, to solve for the energy eigenfunctions in the regions where the potential is constant, and then patch together solutions at these boundaries. We know how to solve for the energy eigenfunctions when the potential is constant. What are the energy eigenfunctions? Yeah, suppose I have a potential which is constant, v is equal to 0. What are the energy eigenfunctions of this potential? Yeah, e to the x. Yeah. And what if I happen to tell you where e per squared, k squared, 1 to n is equal to the energy? Suppose I happen to tell you that here's the potential, and I want to find a solution in this region where the energy is here less than the potential. What are the solutions? That's a second order differential equation. There should be two solutions. What are the solutions of that differential equation when the energy is less than the potential? Decaying Brownian exponentials, exactly. E to the plus alpha x and e to the minus alpha x. And the reason is these are sinusoidal, and these have the opposite concavity. They're growing and dying exponentials. Cool. Okay, so we studied that. Yeah. Oh, shoot, yes, indeed. Sorry.
Oh, okay, good. Thought I was taking crazy pills.
So we know how to solve the energy eigenvalue equation in all these regions where the potential is constant. So our job is going to be to find a solution where we patch them together at these interfaces. We patch them together. What condition should we impose? So the basic condition is going to be continuity. Yeah, of the wave functions fine. So what are the conditions that we need? Well, if v of x, here's the way I like to think about this. Suppose v of x is continuous. Okay. So if the potential is continuous, then what can you say? You can say that phi prime prime is a continuous function times phi of x. So very roughly, if we look at a region where phi isn't varying very much, so if we have a potential that's varying in some way, then phi prime prime in a region where it's not varying much compared to its value, as a function of x, does something smooth because it's varying with the potential. And so phi prime, which is just going to be the integral of this, the integral of a smooth function is again a smooth function. And phi, the integral of that function, is also going to be a nice smooth function. Okay, I've drawn it badly, but... So the key is continuous. Then the energy eigenfunction has a second derivative, which is also continuous. That means its first derivative is continuous, and that means the function itself is continuous.
Oh.
Agree with this? Questions? So in regions where the potential is continuous, the wave function and the first two derivatives all have to be continuous. On the other hand, suppose the potential has a set, v of x, has a set discontinuity. Okay, so the potential does one of those. So what does that tell you about phi prime prime? It's a function of x. So for example, let's look at that first step. Suppose the potential is that first step down by some amount. Then phi.
Okay, so this is saying that it's going to be...
Phi prime is going to decrease precipitously at some point. And the actual amount that it decreases depends on the value of phi. The change in potential times the actual value of phi. And if that's true of phi prime prime, what can you say of phi prime? So this is discontinuous. Okay, phi prime of x, however, is the integral of this discontinuous function. And what does it do? Well, it's linearly increasing in this region because it's derivative, it's constant. And here it's linearly increasing less. So it's not differentially smooth, but it's continuous. And then let's look at the actual function phi of x. Okay, what is it doing? Well, it's quadratic. And then here it's quadratic a little less afterwards. But that's still continuous because it's the integral of a continuous function. Recall that? So even when we have a step discontinuity in our potential, we we still have that our derivative and the value of the function are continuous. Yeah? However, imagine the potential has this delta function, which is what happens when the delta function singular really badly discontinuous. Then what do you say about phi prime prime as a function of x? So it has a delta function, right? So the phi prime has to look like, something relatively slowly varying, and then a delta function. So what does that tell you about the derivative of the wave function? It's got a step function, exactly, because it's the integral of this, and the integral is 0 to 1. Whoops, I missed. So this is a delta, this is a step. And then the wave function itself is, well, it's the integral of a step, so it's continuous. Sorry? It's certainly not differentiable. Its derivative is discontinuous. Well, it's differentiable. Its derivative is not smooth. It is not. So this is continuous. So we've learned something nice. That unless our potential is so stupid as to have delta functions, which sounds fairly unphysical, we'll come back to that later in today's lecture. Unless our potential has delta functions, the wave function and its first derivative must be smooth. Yeah? This is just from the energetic value equation. And we actually argued this from the well-definedness and the finiteness of the expectation value of the momentum earlier in the semester. I wanted to give you this argument for it. It's going to play a useful role. And it also tells us that if we do have a delta function singularity in the potential, then the upshot is that the wave function is going to be continuous, but its first derivative will not. Its first derivative will jump at the wave function. And that means that the wave function, we draw this slightly differently. The wave function will have a kink. Its derivative will not be continuous. Okay? So anywhere we have a delta function in the potential, we will have a kink in the wave function, where the first derivative is discontinuous. Cool? Yeah. That's an excellent question. So what do you expect to happen at such a point? Yeah, exactly. So we're gonna have some pathologies with expectation values of the momentum. Let's come back to that when we talk about delta function potential, which should be at the end of the day. Hold that question in the back of your head. It's a good question. Other questions? Okay, so what we're gonna do now is we're gonna use math to find the energy eigenfunctions and eigenvalues for the finite well potential. I.e., we're going to solve this equation contingent on the boundary conditions that the wave function and its derivative are smooth everywhere. And in particular, they must be smooth here and here. I mean, they gotta be smooth everywhere. We know what the solution is inside here. We know what the solution is in here. All we have to worry about is what happens at the interface. And we're going to use the smoothness of the wave function and its derivative to impose conditions that allow us to match across that set. Everyone cool with that? Okay. So let's do it. By the way, just a quick side note. Let me give you a definition. I've used this phrase many times, but I haven't given you a definition of it. So I've used the phrase bound state, and its opposite is called a scattering state. So here's what I mean by a bound state. Intuitively, a bound state, if you think about this classically, imagine I have a potential well and I have a marble, and I let go from here. This marble is bound, right? It's never getting out of the well. It's stuck. Yeah. And so I would call that a bound marble. On the other hand, a marble that I give a huge kick to, right, big velocity so they can get out, well, then it's not bound to this potential well. So I'll call that a scattering state. Just give it a name. In the next lecture, we'll see why we call it a scattering state. The important thing is that bound configurations of a class of potential are things basically in the well that are stuck. Okay, so the quantum version of that statement is the following. Suppose I take this potential and treat it quantum mechanically, and I consider a state with total energy like this. Well, among other things, the total energy is less than the value of the potential asymptotically far away. So what is the form of the wave function in this region with this energy? Exponential, right? It's e to the minus some alpha x, where alpha squared is roughly the difference of x. And now here, it's going to be e to the plus alpha x. Right? And that's for normalizability. We want to have a single particle in this state. So what that tells us is that the wave function falls off in these classically disallowed regions exponentially. And so the probability of measuring the particle at an arbitrarily far position goes to 0. And it goes to 0 exponentially rapidly. Cool? So I will call a bound state, a quantum bound state, an energy eigenstate such that the probability falls off exponentially as we go far away from wherever we think is an interesting point, like the bottom of the well. Cool? A bound state is just a state which is exponentially localized. If you put it there, it will stay there. Yeah? And it's important that when I say a bound state, I'm talking about energy eigenstates. And the reason is this. Bound state equals energy eigenstate. The reason is that, consider by contrast a free particle. So a free particle with constant potential. What are the wave functions? What are the energy eigenfunctions? Well, they're plane waves. Right? So these are these bound states? No. Good. Okay. On the other hand, I claim that I can build a wave packet, a perfectly reasonable wave packet, which is a Gaussian. Okay. This is some wave function, sine x, and sine 0. Okay, it's a Gaussian, it's nice and narrow. Is that a bound state? Well, it's localized at this moment in time, but will it remain, and in particular its probability distribution, which is this thing norm squared, is localized in space. Sorry, this was 0. It's localized in space, probability being out here is not just exponentially small, it's Gaussian, so it's even minus x squared. It's really not out here. But what happens if I let go? What happens if I let the system at time t? It's going to spread out, it's going to disperse. We're going to talk about that in more detail later. So it's going to spread out, and eventually it will get out arbitrarily far away, with whatever probability you like. So this is not a probability distribution, it's not time invariant. That is to say, it's not a stationary state, it's not an energy eigenstate. Saying something is bound means that it never gets away. So bound states are specifically energy eigenstates that are strictly localized and fall back at least exponentially if we go away from the origin. Cool? Just turn on what do you mean by bound state? Okay, so let's talk about the fine well. So I need to give you definitions of the parameters. Let's draw this more precisely. To give my well, asking about the potential is 0. So potential depth I'm going to call minus V naught. Okay, and I'm going to center the well around 0, and I'll call this side minus L and L. Okay. And I want to find bound states of this potential, just like we found bound states of the harmonic oscillator, i.e. states with energy E, which is less than 0. So these are going to give us bound states, because we're going to have exponential fall-offs far away. So a couple of things to note. The first is, on I think problem set 3 you showed, you showed that if you have a potential which is symmetric, which is even, under x goes to minus x, then every energy eigenfunction, or at least every bound state energy eigenfunction, can be written, well, every energy eigenfunction can be written as phi e symmetric or phi e antisymmetric. So it's either even or odd. I'll just write it. It's either even or odd under the exchange of x minus x. So when a potential is symmetric, the wave function is either symmetric, the energy eigenfunction is either symmetric or antisymmetric. Okay. So we want to solve the actual eigenfunctions, so we want to solve that equation. And we have this nice simple fact that we know the solutions in this region, we know the general solution in this region, we know the general solution in this region. So we're going to call these regions 1, 2, and 3. Just think of the name. So in region 1, that's actually sort of stupid. Let's call this inside, left and right. Okay, so if so let's look at this equation. We have two cases. If the energy is greater than the potential in some region, then this is of the form phi prime prime is equal to energy greater than potential. This is a negative number, and so this is a minus k squared phi. We got exponentials, and if on the other hand E is less than v of x, then phi prime prime is equal to plus alpha squared phi. And in particular here, I want that k squared is equal to 2m upon h bar squared. It's just the coefficient, v minus e, and alpha squared is equal to 2m over h bar squared, e minus v. Okay, so let's apply that here. So in this region, we're going to get oscillations, because we're in a classically loud region where the energy is greater than the potential. So we'll get oscillatory solutions, and the salient fact value of k inside is k is equal to the square root of 2m over h bar squared times v minus e. So that's minus v naught. What did I do? I did this. It's e minus v. Thank you, yes. Minus v. And then we'll get over the alpha. Good. Excellent. So root 2 over h bar squared, and now we have e minus v naught, which is e, the actual value of e, which is negative, right? But the minus v naught or plus v naught is positive, and greater in magnitude. So this is a nice positive number, and k is the square root of it. This is controlling how rapidly the wave function oscillates in this region. Similarly, out here we have alpha is equal to, well, here the potential is 0, so it's equally easy. Alpha is equal to the square root of 2m upon h bar squared. Now v minus e is 0 minus e, which is a negative number. So we can just write e absolute value. So we can write the general solution of this eigenfunction, of this eigenvalue equation, as phi e of x is equal to, let's break that into inside and outside. Well, inside, we know we get, since it's constant with this value of k, we get superpositions of oscillatory solutions. It's the singular difference equation. There are two solutions and two integration constants. So first, we have a cosine of kx plus b sine kx. This is inside. And then on the left, we have a combination of exponentially growing and exponentially decreasing. So the exponentially growing is e to the alpha x plus d e to the minus alpha x. And on the right, similarly, by symmetry, we have some combination of E, but I don't want to call it the energy, so I'll call it a curly E. Alpha to the, or sorry, E to the alpha x plus F E to the minus alpha x. Okay, so that's the general solution. We've solved the problem as a superposition of the two oscillatory solutions or a superposition of the two exponentially growing and damped solutions, or exponentially growing and collapsing functions on the left and right. Questions? So a couple of things to note at this point. So the first is, we have boundary conditions to impose. We have boundary conditions at these two interfaces, but we also have boundary conditions off at infinity. What are the boundary conditions at infinity? Yeah, exactly, it should vanish, so we want the system to be normalizable. Okay, so normalizable is going to say that phi goes to 0 at minus infinity. Phi of x goes to minus infinity goes to 0, actually equals, and phi of x goes to plus infinity should also be 0.
Oh, fine, that's
okay. And then we're also going to have the conditions at the left boundary, and we're going to have conditions at the right boundary. All right. So what are the boundary conditions at the left boundary condition? So first off, what are the boundary conditions we want to impose at the left and right boundaries? Continuous, and the derivative should be continuous. Exactly. So we have that phi is continuous, and phi prime, good God, phi prime is continuous. Similarly, phi continuous, phi prime continuous. Okay. Do we have enough boundary conditions to specify our function? So we have, now for our solution, we have 6 undetermined coefficients, and we have 6 boundary conditions, so that looks good. Are they all independent? Ponder that one. So, in particular, let's start with the normalizable. So in order for phi to go to 0 at minus infinity, d on the left, what should be true? Yeah, d goes to 0. Oops, equals 0. Okay, and on the right? Yeah, that curly E equals 0, which is nice, so I don't ever have to write it again. So that's 0. And that's 0. Okay, that's good. We can take advantage, though, of something nice. We know that the wave function has to be either symmetric or anti-symmetric, right? So we can exploit that and say, look, the wave function is going to be, this is different from our boundary conditions, but it's a true fact, and we can take advantage of it. We can use the parity of the well. So we can use the parity of the potential to say that the system is either symmetric or anti-symmetric. And these are often set as even or odd because the function will be as a function of x, either even or odd. It will either pick up a minus sign or a plus sign under taking x to minus x. So if the system is even, what can we say about these coefficients? What must be true of b, for example? Yeah, so b equals 0. And what else? C equals f. Yeah, good. Okay, C equals f. And if the system is antisymmetric, then A is equal to 0. And we see that C is equal to minus F. Yeah? So that's a useful simplification. So it's easy to see that we could do this either way. We do either symmetric or antisymmetric. I'm going to, for simplicity in lecture, focus on the even case. B is equal to 0, and C is equal to minus F. Or F is equal to, sorry, C is equal to F, so plus C. Okay. So now we're specifically We're specifically working with the even solutions. And on your problem set, you'll repeat this calculation for. So we're going to focus on the even solutions. And now what we have to do is we have to impose the boundary conditions for phi and phi prime. So that's easy enough. We have the function. All we have to do is impose that the values are the same. So, for example, let's focus on the left boundary conditions. So this is x is equal to let's focus on the right, because I don't want to give that minus sign. So let's focus on the right boundary condition. So this is x is equal to plus L. Okay. So when x is equal to plus L, what must be true? Phi and phi prime must be continuous. So what's phi? So phi is equal to, well, from inside, it's a cosine of KL. Yeah. And B is gone because we're looking at the even functions. On the right, however, it's equal to C e to the minus alpha L. Because we're evaluating at the right boundary. Yeah. Okay, so this is cool. It allows us to determine C in terms of A. And if we solve that equation for C in terms of A, we'll get an eigenfunction, phi even, with one overall normalization coefficient, A. And then we can fix that to whatever it has to be so that everything integrates to 1. Yeah? So that seems fine. It seems like we can solve for C in terms of A. C is equal, this is weight. Okay, so C is equal to A cosine e to the plus alpha L. On the other hand, we also have a condition on the derivative. And the condition on the derivative is that phi prime is continuous, and the derivative of this, well, that's easy. It's derivative of cosine. So this is going to be minus sine, but we pull out a factor of k, because we're taking derivative with respect to x. Minus k is sine of kx, evaluated in L, sine of kl, whoops, L. And this is going to be equal to minus alpha c e to the minus alpha L. Oh, yes, there should be an A. Thank you. Okay, so, but now we've got a problem, because this says that C is equal to minus A times K over alpha sine of KL times e to the alpha L. And that's bad, because C can't be equal to two different numbers at the same time. There's a certain monogamy of mathematical equations. It just doesn't work. So how do we deal with this? Well, let's think about what these equations would have meant. Forget this one for the moment, and just focus on that first expression. I'm going to rewrite this slightly. A cosine of KL. Okay. So what does this expression say? Well, it seems like it's just saying we can, if we fix C to be equal to this value for fixed values of kappa, L, and alpha, then there's a solution. However, K, what is K? What are K and alpha? K and alpha are functions of the energy. So it would seem from this point of view, like for any value of the energy, we get a solution to this equation. Everyone see that? But we know that can't possibly be right, because we expect the solutions to be discrete. We don't expect any value of energy to lead to a solution of the energy eigenvalue equation. There should be only a discrete set of energies. Yeah. You do. Thank you. The sign cancel. Yes, excellent. I've never written this equation in my life, so thank you. Yes, extra minus sign. So what's going on here? Well, what we see is that in order to be, we've written down the general form of the solution. Here we're imposing that we've already imposed a condition that we're normalizable at infinity. Here we're imposing the continuity condition on the right. And if we impose just the continuity condition for the wave function, we can find a solution. Similarly, if we pose only the continuity condition for the derivative, we can find a solution for arbitrary values of the energy. But in order to find a solution where the wave function and its derivative are both continuous, it can't be true that the energy takes just any value, because it would tell you that C takes two different values, right? So there's a consistency condition for what values of energy, or equivalently for what values of K and alpha, are these two expressions equal to the same thing? Cool? So we can get that by saying, look, we want both of these equations to be true. And this is easy. I can take this side, this equation, and divide it by this equation, and I will lose my coefficient C, I will lose my coefficients A. What do we get? On the right-hand side, we get, and I'm going to put a minus sign on everything. So minus, minus, minus. So if we take this equation and we divide it by this equation, on the right-hand side, we get alpha, because the C exponential drops off. And on this side, we lose the A, we get a K, and then we get sine over cosine of KL, also known as tangent of KL. Here we have a KL, here we have a K. These are all dimensionful things. Let's multiply everything by an L. And this is nice and dimensionless. Both sides are dimensionless. So we get this condition. This is the consistency condition, such that both the wave function and its derivative can be continuous at the right boundary. Okay? And this is a pretty non-trivial condition. It says, given a value of K, you can always determine the value of alpha, such that this equation is true. But remember that K and alpha are both known functions of the energy. So this is really an equation, a complicated nonlinear equation for the energy. So this is equal to horrible expression, a condition, badly nonlinear, in fact, transcendental condition on the energy. And where is this coming from? It's coming from normalizability and continuity everywhere. And a useful thing to check, and I invite you to do this on your own, is to check that the boundary conditions at the left wall give the same expression. Yeah. Yeah, and it'll be a little more obvious in a second, but here's the reason. So let's divide through by L. This is the form that we got. What are the units? What are the dimensions of this expression? So K is a wave number, so it has units of 1 upon length, right? And that's good because that's 1 upon length times the length, and you better have something dimensionless inside a tangent. But it seems, so there are two things to say about this. The first is it seems like L is playing an independent role from K in this equation. But this is dimensionless. These are both dimensional with units of 1 upon length. So we can make the entire expression dimensionless, and to make it clear that K and L don't have an independent life, the dimensionless quantity KL times the tangent of that dimensionless quantity is equal to this dimensionless quantity. So the reason that this is preferable is twofold. First off, it makes it sort of obvious that K and L, you can't vary them independently in this sense. But the second is that the second is that it makes it nice and dimensionless, and you always, whenever possible, want to put things in dimensionless form. I mean, it's just multiplying by L, so it's obviously not all that deep, but it's a convenient bit of multiplication by L. Other questions? Okay. So, where are we? So I'd like to find the solutions of... Let me write this slightly differently. Where? Good. K squared is equal to 2m upon h bar squared v naught plus e, and alpha squared is equal to 2m upon h bar squared e, the positive value v. So this is really complicated expression as a function of v. So I'd like to solve for the actual energy eigenvalues. I want to know what are the energy eigenvalues of the bound state as a function of L, for example. Sadly, I can't solve this equation. It's a transcendental equation. It's a sort of canonically hard problem to solve. You can't write down closed form expressions for it. However, there are a bunch of ways to easily solve it. One is take your convenient nearby laptop, open up Mathematica, and ask it to numerically find solutions to this. And you can do this. It's a good exercise. I will encourage you to do so on your problem set. And in fact, on the problem set, it asks you to do a calculation, and it encourages you to do it using Mathematica. Let me rephrase the statement in the problem set. It would be crazy for you to try to do it only by hand. You should do it by hand and on computer because they're both easy and you can check against each other. They make different things obvious. You should all start, this should be your default, is to also check on Mathematica. The second thing we can do is we can get a qualitative solution to this equation just graphically. And since this is such a useful technique, not just here, but throughout physics, to graphically solve transcendental equations, I'm going to walk through it a little bit. So first, this is going to be the graphical solution. And we can extract, it turns out, an awful lot of the physics of these energy eigenfunctions, energy eigenstates, and their energies through this graphical technique. So the first thing is I wrote this in nice dimensionless form, and let me give those dimensionless variables name. Let me call KL is equal to Z, just define a parameter Z, and alpha L is the parameter Y. Okay. And I want to note that Z squared plus Y squared is equal to a constant, which is, I will call, if you just plug these guys out, K to KL squared plus AL squared, that's easy. KL squared is this guy times L squared. AL squared is this guy times L squared. And so the E and minus E cancel when we add them together. So we just get 2m v naught over h bar squared times L squared. So 2m upon h bar squared, L squared, v naught. And I'm going to call this R naught in something of pathological abusive notation. Okay, so this is our expression. And actually I want to call this R naught squared. I know, it's awful. But the reason I want to do this is that this is the equation for a circle. Yeah? And a circle has a radius. The thing that goes right here is R squared. Okay, so this way you're thinking, come on, circle. So let's plot. Now, how are we going to solve this equation? Here's what I want to solve. I have now two equations relating Z and Y. We have that from this equation, Z tangent Z is equal to Y. And from this equation, we have that Z squared plus Y squared is a constant, R naught squared, where R naught squared depends on the potential and the width in a very specific way, the depth of the potential and the width of the area. So we want to find, simultaneously, we want to find simultaneous solutions of these two equations. Yeah? So that's relatively easy. So here's Y, and here's Z. So this equation has solutions anytime the Y plus Z squared is equal to R naught squared. That means anytime we have a circle. So solutions for fixed values are not Y on circles. Oh, I really should have drawn this under here. Sorry. Y and Z. Okay, so those are the circles. Notice that I'm only focusing on Y and Z, both positive. Y. Not Y, Z, but WHY. Why am I focusing on the variables Y and Z being positive? Because we started out defining them in terms of K and L, which were both positive, and alpha and L, which were both positive. Can we find solutions to this equation that have X and Y negative? Sure, but they don't mean anything in terms of our original problem. So to map on this solution to our original problem, we want to focus on positive values Y and Z. Cool? Okay, so that's this one. The solutions lie on a circle, so given a value Y, you can find a solution of Z. But we want to also find a solution of this equation. And this equation is a little more entertaining to plot. Here's Y, here's Z. So what does Z tangent Z do? Oh, shoot. I want to plot Y vertical, otherwise it's going to be a giant pain. Happily, this plot can be left identical. Let's plot Y vertically. So the reason I want to plot Y vertically is that this is Z tangent Z. So first off, what does tangent Z look like? Yeah, this is awesome. Yeah, it looks like this. Yes, exactly. So tangent is sine over cosine. Sine is 0 and cosine is 1. So it does this as you go to a value where the argument, let's call the argument Z. So if we just plot tangent. Okay. So when Z is equal to pi over 2, then the denominator cosine vanishes and that diverges. Oops. Okay, so here's pi over 2, here's pi, oops, pi over 2, and here's 3 pi over 2. And so now we're only interested in the first quadrant, so I'm going to just ignore down here. Okay, so this is pi over 2, this is pi, 3 pi over 2. But this is not what we're interested in. We're not interested in tangent of Z. We're interested in Z tangent Z. And what does Z tangent Z look like? Well, it's basically the same, right? Because Z tangent Z has an extra factor of 0 here, and it remains extra small at the beginning, but it still curves off roughly like this. And Z is just nice and constant, nice and linear, nice and regular throughout this. So it doesn't change the fact that we have a divergence at pi over 2. And it doesn't change the fact that it vanishes again at pi and becomes positive again. It just changes the shape of the curve. And in fact, the way it changes the shape of the curve is this becomes a little fatter around the bottom, it's a little more round. And when we get out to large values of Z, it's going to have a more pronounced effect because that slope is, at every example where it crosses 0, that slope is getting larger because the coefficient of Z is getting larger. So it's just going to get more and more sharp. But anyway, with all that said, here's 0, here's pi over 2, or sorry, pi over 2, here's pi, here's 3 pi over 2. The second plot we want to plot, y is Z tangent Z, we know how to plot this. So are simultaneous solutions of this. Values of y and z for which this equation is solved and this equation is solved for the same value. This is the graphical solution. So let's combine them together. And the line plots look like this. First we have I reduce. So let's plot the tangents. Okay. And then we have these circles for various different values of r. So for a particular value of r, for example, suppose this is the value of r. This is r naught. So how many solutions do we have? One set of common points where y and z solve both equations. So we immediately learn something really lovely. What happens to the radius of that circle as I make the well deeper? Yeah, as I make the well deeper, that means v naught gets larger and larger eventually, the radius gets larger. So to make the well deeper, I make the circle larger. Will I still have a solution? Yeah, I'll still have a solution, but check this out. Now I'll have a new solution. Yeah. And you can even see the critical value of the depth and the width of the well. In order to have exactly a new bound state appearing, what must the value of r naught be? Well, it's got to be that value such that r naught squared is pi. Yeah. And similarly, we answer the following question. As I make the well deeper and deeper and deeper, holding the width fast, as I make it deeper and deeper, does the number of states increase or decrease? It increases. We make it deeper and deeper, that way the radius of that circle is getting bigger and bigger. There are more points where the circle intersects this point. So here's another one. Okay, we got one here, one here, one here, 3 solutions. And the number of solutions just keeps every time we click over a new point. By increasing the radius of the circle, we get a new solution. We get another bound state. But here's the thing that I really want to focus on. Let's make the well less and less deep. Let's make it shallower and shallower. At what depth do we lose that first bound state?
Never.
We never do. Right? There is no circle so small that it doesn't intersect this curve. In a 1D finite well potential, there is always at least one bound state. There are never 0 bound states. This will turn out not to be true in 3 dimensions, which is kind of interesting. But it is true in 1 dimension that we always have at least one bound state. And in fact, you can decorate this. You can use this and fancy it up a bit to argue that in any potential in 1D, there's always at least one bound state. Unless the temp is constant. Any potential that varies and goes to 0 infinity. Yeah? And so we still don't have any numbers, but we know an awful lot about qualitative structure of the set of energy eigenvalues, of the spectrum of the energy. Yeah? Great, so when you have 2 solutions, what does that mean? Well, you've got 2 bound states, 2 different energies. Right? Every solution here, it's a good question, every solution here corresponds to some particular value of y and some particular value of z. Those values of y and z are just telling you what k and alpha are. And so that's determining the energy. So a different value of k is going to give you a different value of the energy. So we just eyeball this in particular. Let's look at alpha. Alpha is just E. Alpha squared is just E. Yes? So here's a quick question. If alpha is just E and alpha L is y, so this is our y value. Y is roughly alpha modulus the width, which means it's roughly the energy, square root. So this value, the vertical value of each of these intersection points on a given circle, corresponds to the square of the energy times the coefficients. So which state has the largest value of the energy? Absolute value. Which state is most deeply bound on this circle? Yeah, the first one, right? Because it's the largest value of alpha. So this is nice. We see that the first state always has a higher value of alpha than the second state, which always has a higher value of alpha than the third state. And every time we add a new state, we make the depth of these guys, the energy, binding energy of the already existing states, we make it just a little bit deeper. We make it a little more tightly bound, and only eventually then do we get a new bound state appearing. And what's the energy of that new bound state when it appears? 0 energy. It's appearing just at threshold. Okay. So we'll explore that in more detail in the problem set, but for now, we'll leave it at that. Questions? Other questions? Yeah. Yeah. Excellent question. What about this one? We're going to come back to that in just a few minutes. It's a very good question. So the question is, look, if any potential that goes to 0 infinity wiggles inside, if any potential like that 1D has a bound state, what about the delta function? We briefly talked about that. So we're going to come back to that in just a few minutes. But it's a prescient question. Okay, other questions? Yes. Thank you. Okay, good. So let me talk about that in a little more detail. So I was going to go into this, but so a new bound state appears. So let's consider a point where our R naught is just, let's say, it's just the right value so that R naught is equal to pi. Okay, and we see that we're just about to develop a new bound state. So let's think about what that bound state looks like. So this is the new bound state. And I'm going to put this in parentheses because it's got bound state. And we say at threshold. Okay, at threshold, i.e. at the energy is roughly 0. And R naught is equal to pi. Okay, so this is really what we need. This new state when R naught is pi, and we have a solution on that second branch. Cool? So what does this wave function look like? What does it look like when you have a wave function that just appeared? It's just barely bound. Well, first off, what does it mean to be bound? Let's just step back and remember for a minute. What does it mean to be a bound state? It means your energy eigenfunction and you're localized. Your wave function falls off at infinity. Now, if it falls off at infinity, do these guys fall off at infinity? These wave functions? Sure, they fall off with an exponential damping. And if you let's look at the right-hand side of the well. This new bound state is appearing just at 0 energy. So out here, what is the wave function? It's e to the minus alpha x. Well, what's alpha? 0, right? There it is, 0. So this is E minus alpha x with alpha is equal to 0. This is constant. So what does the wave function look like? Well, the wave function, again, over the same domain, here's 0, L. So we know that in this domain, and here's the value 0, we know that in this domain it's oscillatory, and in this domain it's constant. And actually, since we know that it's the first excited state, we know that it does this. So if we make the well, ever so slightly deeper, okay, which means making the radius of the circle ever so slightly larger, we will get a non-zero value for the alpha of the solution, right? It'll be just tiny, but it'll be non-zero. So we make the well just a little tiny bit deeper, we get something, okay, good. So what's going to happen to the wave function? Well, instead of going flat, this is going to curve just, it's got a little more energy, there's a little more curvature, so it curves just a little tiny bit more, and then it matches on to a very gradually decaying exponential. Okay, so what's happening as we take this bound state, the second bound state, and we make the well a little more shallow? We make the well a little more shallow, it's a little less curved inside, and the evanescent tails, the exponential tails, become longer and longer and longer and broader until they go off to infinity, until they're infinitely wide. And is that normalizable anymore? No, that's not normalizable. So the state really isn't strictly localized at that point. It's not really a normalizable state. And just when the state ceases to be normalizable, it disappears. We make the well just a little deeper and there's no state there at all. Okay, so this tells you a very nice thing. It's a good bit of intuition that when states are appearing or disappearing, when states are at threshold, as you vary the depth, those threshold bound states have exceedingly long evanescent tails, and they're just barely bound. Okay, this turns out to have all sorts of useful consequences, but let me look at that. Did that answer your question? Good. Yeah.
So this often varies, as you say, proportional, right? So, but also, we have this intuition that as the increase the length as well, the energy is going to decrease.
Fantastic. Okay, what's up with that? Right. So the question is this: we already have intuition that if we take a finite well and we make it a little bit wider, the ground state energy should decrease. The energy of the ground state should get deeper and deeper. The magnitude should decrease. Right? That was our intuition. So let's check if that's true. What happens if I take the ground state and here for some value of the radius, and then I make the well? Well, if I make the well a little bit wider, what happens to R naught, the radius of the circle? Well, if I double the length of the well, the width of the well, then it'll double R naught. It'll double the radius of the circle. So if I make it wider, R naught gets bigger, we go to a bigger circle. And what happened to the energy of the state? Yeah, it got deeper and deeper and deeper. Yeah. And meanwhile, as we make it wider, we make the well wider, the circle is getting bigger again, and we're going to get more and more states. So as we make the well wider, holding the depth fixed, we get more and more states. As we make the well deeper, holding the width fixed, we get more and more states. And so how do you trade off and make it twice as wide? How much? So here's a good question. Suppose I take a well, and it has n states. Suppose I then make it twice as wide. What must I do to the energy so that it still has the same states with it?
You make it twice as wide, what would you have to do to the energy to make it have the same states? Where are we getting this R squared? I'm not sure.
Yeah, exactly. Got to divide it by 4. So like double the length. That means the radius is divided by 4.
Well, L squared is in there.
Well, that's almost true. So if I put a factor of 1/4 here, that's almost true, except for the value of value of y is unchanged, but the alpha hasn't changed. Or the alpha has changed because there's an L. So y is fixed, but alpha's changed because of the L. So the reason that it's useful to write things in these dimensionless forms is that you can see the playoff of the various different dimensional parameters in changing the answer. Other questions? Okay. So a couple of comments. So the first is, let's just check to make sure that this makes sense. We've already solved this problem. We solved this problem a while ago, but we solved it in a particular limit. We solved it in the limit that the potential is arbitrarily deep. Okay. So So when the pendulum was arbitrarily deep, holding the width fixed, that was the infinite well. That was the first problem we solved. So let's make sure that we recover this in that limit. So what happens as we make the well arbitrarily deep, holding the length fixed, the width fixed? So if we make this arbitrarily deep, it's getting arbitrarily large. That means R naught is getting large. We've got a huge circle. So what do these solutions look like when we have a huge circle? We're going to do that here. We do that here. So if we make the pendulum nice and deep, let's think about what that plot looks like. So again, that first plot looks identical with the tangents.
So let's see if I can answer this. We've got RZ, Y, and Z. The length hasn't changed, K shouldn't change. That's just going to be the alpha that changes. So this KL we're going to get something like this. Yeah. And as V0 goes to alpha goes to infinity, so we have y goes to infinity, and y goes to infinity. This is not going to be a radius, it's just going to be a line, right? Because it's going to be no, y goes to, yeah. So y goes to 0? I think my intuition is saying that this is going to be like this, right? No, it'd have to be the other direction because more than one state. Alpha goes to infinity, y goes to infinity. It's probably going to be like this, no? I think.
So on and so forth. And what I want to do is I want to... Okay, so this is way up there. So these guys are basically verticalized at this point. So for very, very large values of y, and in particular for very large values that are of order the gigantically deep radius are not, what does the circle look like? So what does the second equation look like, the second curve? Well, again, it's circles, but now it's a gigantic circle.
Okay.
Yeah, exactly. It's a gigantic circle. It's basically flat. It's not exactly flat, but it's almost flat. It's a circle. So what are the values? And here's the key question. What are the values of yeah, okay, good. So what are the values of the curve where we get a solution? The values now of z. The values of z are just exactly on these vertical lines on the separator sheets. The value of z is at pi over 2 and pi. Pi over 2 and 3 pi over 2. And then another one at 5 pi over 2. And so on and so forth. Right? So what we find is that the allowed values of z sorry, Caleb. Yes, good. The allowed values of z are equal to n2n plus 1 over pi. Whoops. Oops, 2 plus 1 over 2 is pi. So let's just check that. So n is 0, that's 0, 1/2 pi. N is 1, that's 3/2 pi. Good. So these are the values of z, which says that KL is equal to 2n plus 1 upon 2 pi. Or K is equal to 2n plus 1 over 2L, which is the width of this well, because it's from minus L to L. Pi. So is this the correct answer for the infinite square well? Are these the allowed values of K inside the well for the infinite square well? Almost. Instead of 2n plus 1, it should just be n plus 1. We seem to be missing about half of the energy eigenvalues. Yeah, thank you. This is only the even ones. We started out saying, oh, look, let's look only at the even ones. Where do you think the odd ones are going to be? Well, that's n, so the odd ones, this should be k even. So what about k odd? Well, we know the answer already. Oops, odd. It's odd spelling. Should be equal to 2n over 2l plus 2 over 2l. Whoops, 2 capital L. Pi. Okay, this is our guess, just from matching onto the infinite square well. So what does that mean? Well, that means it should be this one and this one. So when you go through this exercise on your problem set and you find the solutions for the odd, when you repeat this analysis for the odd ground states, what should you expect? Well, you should expect to find this. And what do you think the curves are that you're going to use, that you're going to find, that you're going to use in the graphical solution to your transcendental equation? Yeah, it's really tempting to say, oh, it's just going to be something shifted like this. Okay, so these are going to be the odd. Question mark, question mark. Okay, so you'll check whether that's correct intuition or not on your problem. Okay, questions? Yeah. Excellent. So that's a really good question. So how to say, what we've done here, to make this an infinite well. So the question, let me just repeat the question. The question is, look, what about all the other states? We know this, it's true that R0 is gigantic, but eventually we'll go to a large enough Z where it's the circle coming down over here too. So what's up with that? What are those states? Where are they? What do they mean in terms of the infinite square well? Well, first off, what are the energies of those states? Yeah, they're very low in magnitude, which means they're close to what in absolute value? 0. They're close to 0. So they're at the top of the finite well. And these are the states bound at the top of the finite well. These are the states bound at the bottom of the finite well. But how many states are bound at the top of the finite well when we take a limit that the well goes infinitely deep? Yeah, none of them, right? So when we make the well infinitely deep, what we're saying is, pay no attention to the top of the well. Look only at the bottom of the well. And if it's really deep, yeah, it's a pretty good approximation. So that's what we're doing. We're saying, look, pay no attention. There is no top of the well. There's just the bottom. And look at the energy eigenvalues. Does that make sense? So what we're saying is if you have a preposterously deep well, the energies of a preposterously deep well should be a good approximation to the low-lying energies of an infinitely deep well. Because, it's way up there. What difference could it make? And that's what we're seeing work out. Did that answer your question? Yeah, okay, good. So this is we're good at intuition. So when we say this is the energy 0, and the potential has a minimum at minus V naught, then, and we're measuring the energy relative to 0, then the top of the potential well are states with energy close to 0. And the states at the bottom of the potential well are those states with energy of order V naught. Cool. And what are the energies of all these states? The order V naught. Okay. Because this is exactly V naught? No, because this isn't linear, it's actually a circle. So there's going to be a correction. The question is going to be quadratic. If you work out that question, correct. The depth above the bottom of the potential is correct for the energy of the corresponding well. Hopefully that's used in exercise. Other questions? Okay. So there's another limit of this system that's fun to think about. So this was the infinite well limit. What I want to do, I want to take advantage of the observation we made a second ago, that as we make the well deeper, we get more states. As we make the well more narrow, we get fewer states. To trade that off, consider the following limit. I'm going to take the potential well, okay, which has a particular just a ground state that looks like, what does the ground state look like? So the ground state wave function is going to be x. So here's 0, and here's exponentially growing, here's exponentially decreasing. If the ground state, how many nodes will it have inside? How many nodes will the ground state have? 0. Good. Okay.
That's here.
So there's the ground state looks something like this. We more conventionally draw it like this, but just for fun, we draw it in this fashion. In particular, it has some slope here, and it has some slope here. Oh shit! Did I? Yes, I did. Damn it! I just erased the thing that I wanted to hold on to. Okay, so there's our wave function. It has some tubular slope here, and it has some tubular slope here. And this is the ground state wave function with some energy. I don't know. I'll call it this. And what I want to do is we've already shown that as we make the well more and more shallow and more narrow, the energy gets closer to the bound state. The ground state gets closer to 0, but there remains always a bound state. There's always at least one bound state. Prove that. Proved. And if it is this way. So I want to do that. I want to take this seriously. But here's the limit I want to consider. Consider the limit that we make the potential V goes to 0. V goes to infinity. Not. While making L go to 0. So what I want to do is I want to take this thing and I want to make it deeper and deeper, but more and more narrow. Okay. If I do this, repeatedly, eventually I will get a delta function. And I'll get a delta function if I hold the area of this guy fixed. Yeah. So if I do so holding the area under this plot fixed, I will get a delta function. Can we recall that? So let's think though quickly about what's going to happen to the ground state wave function. So as I make the potential, let's take this wave function. Let's look at this version of the potential. So as I I make the potential deeper, what happens to the rate of the oscillation inside, or to the curvature inside? So the system is oscillating more, it changes more rapidly, because phi double dot, or phi double prime, is equal to v minus e phi. It oscillates more rapidly. So we make it deeper, the system tends to oscillate more rapidly. However, as we make it more narrow, the system doesn't have as far to oscillate. Right? So it oscillates more rapidly, but it doesn't oscillate as far. So what's going to happen? Well, as we make it more and more narrow and deeper and deeper, you again have the wave function coming in, and now it oscillates very rapidly. Let's do it again. The wave function comes in, and it oscillates very rapidly, and then it doesn't tail out. And now, as we have a delta function, exponential damping, it oscillates extremely rapidly over an arbitrarily short distance, and gives us the kink that we knew at the very beginning we should expect when the potential is a delta function. Right? From our qualitative structure of the wave function, at the very beginning, we saw that when we have a delta function potential, we should see a kink in the wave function. Because, again, if we have phi prime prime is discontinuous, or this delta function is discontinuous, phi prime is the integral of this is a step, and phi is continuous. So here we have a step function, we get a discontinuity in the second derivative. Here we have a delta function in the potential, and we get a discontinuity in the first derivative. We get a kink in the wave function. Yeah. Sorry, say again. For E1? Very good question. So let me do this more seriously. Let's do this more carefully. Consider. So the question is, for the first excited state, do we get a jump? Do we get a discontinuity? What do we get for the first excited state? Right. So let's talk about that in detail. So here's a very good question. Example: V is equal to minus V naught delta of x. Now here I want to just warn you of something. This is totally standard notation for these problems, but you should be careful about dimensions. What are the dimensions of V naught? Parameter V naught. It's tempting to say energy. That's an energy. That's an energy. But wait, what are the dimensions of the delta function? 1 over length, right? Because we know that delta alpha x is equal to 1 over norm alpha delta of x. So if I write delta of x, which is always a slightly ballsy thing to do, because this should really be dimensional, if I write delta of x, then this has units of 1 over length, which means this must have units of length times energy. Okay? Just a little warning, when you check your answers on the problem, you always want to make sure that they're dimensionally consistent, and so it will be important to make sure that you use the energy times the length for the dimensions of that beast. Okay, so my question here is there a bound state? So for this example, for this potential, the delta function potential bound state, which again is this guy, is there a bound state? So again, we can, we just had the intuition for the potential V and deeper V naught divided by epsilon over width epsilon. So V naught, in order for this to be an energy, has to be an energy times length because we're going to divide by length. So this is going to give us a delta function potential limit. We have an intuition that we should get a bound state with a kink, but let's check that intuition. We'll actually solve this problem. So we'll do the same thing we did before. We now write the general solution in the places where the potential is constant, which is on the left and on the right, and then we want to impose appropriate boundary conditions at the interface and at infinity, where these are going to be normalizable, and this is whatever the right boundary conditions are, so we're going to have to derive the appropriate boundary conditions. So let's just do that quickly. So phi with definite E is equal to A. So in this region, in the left, it's either growing or decreasing exponential, so A e to the alpha x plus B e to the minus alpha x, and this is x less than 0, and C e to the alpha x plus D e to the minus alpha x for x greater than 0. So first off, let's hit normalizability. What must be true for normalizability? Yeah, it better be converting to 0 here and converging to 0 here, which means that C had better vanish, and B had better vanish. Okay, so those guys are gone from normalizability. And meanwhile, the ground state is, if this is symmetric, what is going to be true of the ground state? It's going to be symmetric. So A must be equal to D. Great. So A is now just some overall normalization constant, which we can fix for normalization. So it looks like this should be the solution. We have an exponential, we have an exponential. But there's one more boundary condition to fix. We have to satisfy some matching. We have to satisfy the boundary conditions at the delta function. So what are those matching conditions? So we can get that from the Schrödinger equation, from the energy angle equation, which says that phi prime prime is equal to h bar squared on 2m. Sorry, bigger dimensions, right? So it's 2m over h bar squared. V minus E. In this case, V is equal to minus V naught delta function. That's very strange. Yeah, so minus 2m over h bar squared V naught delta of x minus E. I pulled up minus, so plus E. Fine. So this must be true at every point. This, of course, is 0 everywhere except for at the origin. So what we want to do is we want to turn this into a boundary condition. And we know what the boundary condition is. If V is a delta function, that means that phi prime prime is also a delta function, proportional to a delta function. That means that phi prime is a step function. And how did I get that? I got that by integrating phi prime prime. You integrate a delta function, you get a step function. Well, that's cool. How do we figure out what step function discontinuity gives us? Let's integrate. Let's integrate right across the delta function to figure out what the discontinuity is. So let's do this Higgs equation integrated from minus epsilon to epsilon, where epsilon is a very small number. Minus epsilon to epsilon. So what is this going to give us on the left? Well, integral of a total derivative is just the value of the thing at evaluated points. So this is going to be phi prime at epsilon minus phi prime at minus epsilon. What does that mean? The difference between the derivative just after the origin and just before the origin. This is the discontinuity for very small epsilon. This is the discontinuity of the derivative at the origin, at the delta function. And we already expected it to have a step discontinuity, and there it is. And how big is it? Well, on the right-hand side, we have 2m minus 2m on h bar squared. And we're going to get two terms. We had a term from integrating the first term, but over this narrow window around the, let's say epsilon is here, over this narrow window, we can treat the wave function as being more or less constant. But in any case, it's continuous, and this is a delta function. So we know what we get from the integral of the delta function. We just get the value v naught phi at the delta function, phi the zero of the delta function is phi 0. We get a second term, which is plus the energy integrated against phi. The energy is a constant, and phi is continuous. So this, whatever else you can say about it, is roughly the constant value of phi at the origin times the energy times the width, which is epsilon. So plus order epsilon terms. Recall that? So now what I'm going to do is I'm going to take the limit as epsilon goes to 0. So I'm just going to take that, just one, the discontinuity just across 0. So this is going to give me, of this, gives me the change in the slope at the origin. Okay. The derivative just after the origin, minus the derivative just before the origin, is equal to, these order epsilon terms go away, minus 2m upon h bar squared, v naught phi. So that's my continuity, that's the condition for continuity of the derivative and appropriate discontinuity of the first derivative at the origin. And so this, when we plug in these values of this form for the wave function, when we take a derivative, what we're going to do is we're going to pick up an alpha. And so when we work all of this out, I'm not going to go through the algebra. You're going to go through it on the problem set. When we take this condition and we impose this condition with this wave function, it gives us a very specific value for alpha. This is only solvable if alpha is equal to mv naught upon h bar squared. Good. So let's just check the units. So this is momentum times length, momentum times length. This is mass. This is an energy times the length. So this has overall units of overall units of 1 upon length, which is what we wanted. So that's good. So we get alpha is equal to mv naught upon h bar, and that gives us the form of the potential. And it also tells us that the energy, plugging this back in, is equal to minus h bar squared alpha squared upon 2m, which we could then plug in the value of alpha and solve for v naught. So what we found is that there is a single bound state of the delta function potential, which we could have done by just taking this limit. It's a fun way to rederive the same results. It's a nice check on your understanding. So we find that there's a single bound state of the delta function potential. And what about an odd bound state? We assumed at an important point that this was even. What if I assumed that it was odd? One node. What if we assumed that it was odd? What would be true of the wave function? Well, for odd, this would be a and this would be minus a. So the value of the wave function at the origin is what? 0. So that tells us the value of the wave function is 0. What's the discontinuity? 0. So it's as if there's no potential because it has a 0 right at the delta function. Yeah. But that means that this wave function, an odd wave function, doesn't notice the delta function potential. So is there a bound state? No. So how many bound states are there? Always exactly one for the single isolated delta function. On your problem set, you're going to use the result of the single isolated delta function, and more broadly, you're going to derive the result for two delta functions. So you might say, like, why two delta functions? And the answer is the two delta function problem, which involves no math, right? It's a totally straightforward, simple problem. You can all do it right now on a piece of paper. The two delta function problem is going to turn out to be an awesome model for the binding of atoms. And we're going to use it as intuition on your problem set to explain how quantum mechanical effects can lead to an attractive force between two atoms. See you next time.
All right. That is lecture 11. I feel pretty good about that. Let's go to lecture 12. I'm just going to adjust the light here. It's a bit tricky. Getting it so that it's not too blue. Hopefully that showed the lecture. I think sometimes I don't update the send to live thing, so I think I might have missed that one. All right, well, hopefully it's showing. All right, where are we here? I need to find the next lecture.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at www.mit.edu.
All right. Hello. So today, as people slowly trickle in, scattering states. So we spent a lot of time talking about bound states corresponding to particles that are localized in a region and that can't get off to infinity. And I think when we distinguish bound states from scattering states, we're usually talking about energy eigenstates. They're eigenstates that are strictly localized in some region. For example, in the well, all of the states are strictly localized to be inside the well. In the finite well, which we saw last time, there are a finite number of states, energy eigenstates, which are bound inside the well. But there are also states that aren't bound inside the well, as we'll see in recitation. And as we discussed in qualitative structure of wave functions, but energy eigenfunctions. So, why do we really care about the algorithm was next about? So why would we really care about states that are bound from scattering states? And the obvious answer is, I am not bound, right? Most things in the world are either bound or they are scattering states. By scattering states, just means things that can get away, things that can go away. So it's often, it's easy to underemphasize, it's easy to miss the importance of scattering experiments. It's easy to say, look, a scattering experiment is where you take some fixed target and you throw something at it and you look at how things bounce off and you try to do something about this object by how things bounce off. For example, one of the great experiments of our day is the LHC, and it's a gigantic ring. It's huge. One of the Germans outside of Geneva, and those are people, and that's the detector. That's one of the detectors in CMS. And you know, what are you doing in this experiment? This experiment is taking two protons and you're accelerating them ridiculously fast. I'm only going to be like just barely. Until they have a tremendous amount of kinetic energy, and you're colliding into each other. The idea is, if you collide into each other, you watch how the shrapnel comes flying off. You can deduce what must have been going on in the actual collide. You can deduce about structure, how radical that works. And it's easy to think with scattering experiment. That's a bizarre thing that happens in particle detectors under mountains. But I am currently engaged in a scattering experiment. The scattering experiment I'm currently engaged in is light is bouncing from light sources in the room off of various bits of each of you, and some of it improbably scatters directly into my eye. That is shocking. And through the scattering process, and deducing what I can from the statistics of the photons that bounce into my eye, I can deduce that you're sitting there and not over there, right? Which is pretty awesome. So we actually get a tremendous amount of the information about the world around us from scattering processes. These are not esoteric weird things that happen. Scattering is how you interact with the world. So when we do scattering problems, it's not because we're thinking about particle colliders. It's because at the end of the day, I want to understand how surfaces bless you, how surfaces reflect. I want to understand why when you look in the mirror, light bounces back. I want to understand how you see things. So this is a much broader, scattering is a much broader idea than just the sort of legacy of how we study particle physics. Scattering is what we do constantly. Okay, and we're going to come back to the computer in a bit. Let me close this for now. Yes.
Just going to get a little bit more water.
So today we're going to begin a series of lectures in which we study scattering processes in one dimension in various different settings. So in particular, that means we're going to be studying particles being quantum particles being sent in from some distance, incident on some potential, incident on some object, and we're going to ask how likely are they to continue going through, how likely are they to bounce back. Okay. And so we're going to start with an easy potential, an easy object off of which to scatter something, which is the absence of an object, the free particle. And I want to think about how the system evolves. So for the free particle, where we just have something of mass m and its potential is constant, we know how to solve the question. Yeah. Fantastic question. Okay, I'm going to come back to that in just a second. It's a very good question. So we're interested in energy eigenstates, and we know the energy eigenstates for the free particle. We've written these down many times. I'm going to write it in the following form. Suppose we have a free particle in an energy eigenstate with energy E, then we know it's a superposition of plane waves, e to the ikx, plus b, e to minus ikx. And the normalization is encoded in A and B, but of course, these are not normalizable states. We typically normalize them with 1 over root 2 pi for delta function normalizability. Now, in order for this to be a solution to the Schrödinger equation, we need that the frequency, or the energy E, is equal to 8 bar squared k squared upon 2n, and omega is this upon h bar. And knowing that, we can immediately write down the solution, because these are energy eigenstates, we can immediately write down the solution of the Schrödinger equation, which begins at time t0 in this state. Okay, so there's a solution of the time-dependent Schrödinger equation. So we've now completely solved this in full. Generality, which is not so shocking since it's a free particle. But let's think about what these two possible states are. What do these mean? So the first thing to say is, this component of our superposition is a wave, and I'm going to call it a right-moving wave. And why am I calling it a right-moving wave? If you draw the real part of this at some moment in time, it's got some crests. And if you draw it a short bit of time later, I want to ask how the wave has moved. And for example, peak in the wave will be when kx minus omega t is 0. If kx minus omega t is 0, then kx is equal to omega t, or x is equal to omega over kt. And assuming as we have that k is positive, then this says that as time increases, the position increases. And this one, x is equal to x is equal to minus k over omega, so omega over kt. So we'll call this a right going or right moving. And we'll call this a left moving wave. So the general solution is a superposition, an arbitrary superposition of a left moving and a right moving wave. This should be familiar from 803 in your study of waves. But as was pointed out just a moment ago, we've got a problem. Psi e, or phi e, is not normalizable. And this is obvious from, if we, let's set b equals 0 for simplicity, this is a pure phase, and the norm squared of a pure phase is 1. And so the probability density is constant. It's 1 from minus infinity to infinity. So the probability of finding it at any given point is equal. So assuming this is another real line, which what we need by saying it's a free particle, there's no constant you can multiply that by to make it normalizable. This is not a normalizable function. So more precisely, what we usually do is we say, we take our states phi's of k, 1 over root 2 pi, e to the I kx, such that phi k prime is equal to delta. Sorry, this is not quite one, right? Such that, well, phi k prime is equal to delta of k over k prime. This is as good as we can do. This is as good as we can get to normalizing. It's not normalized 1, it's normalized 1 k is equal to k prime to the value of the delta function, which is ill-defined. So we've dealt with this before, we talked about it. So how do we deal with it? Well, we just learned actually a very important thing. This question, very good question, led to a very important observation, which is that can a quantum mechanical particle be placed, meaningfully be said to be placed in an energy eigenstate which is bound? Can you put a particle in the ground state of a harmonic oscillator? Sure, that's right. Can you put the particle in the k equals 7 state of a free particle? No. So these scattering states, you can never truly put your particle truly in a scattering state. It's always going to be some approximate plane wave. Scattering states are going to be some plane wave asymptotically. So we can't put the particles directly in a plane wave. What can we do, however? We can build a wave packet. We can use these as a basis for states which are normalizable and reasonably localized. So we need to deal with wave packets. So today is going to be, the beginning of today, is going to be dealing with the evolution of a wave packet. And in particular, we'll start by looking at the evolution in time of a well-localized wave packet in the potential corresponding to a free particle. And from that, we're going to learn already some interesting things, and we'll use that information for the next several lectures as well. Questions before we get going? All right. So here's going to be my first example. So consider, for the free particle, or consider a free particle, FP, in a minimum uncertainty wave packet. Okay, so what is a minimum uncertainty wave packet? We've talked about the Gaussian, exactly. So the minimum uncertainty wave packet is Gaussian. Suppose that I take my particle and I place it at time 0, x0, in a Gaussian. I'm going to properly normalize this Gaussian. Hate these factors of pi, but whatever. A root pi e to the minus x squared over 2a squared. Okay, so this is the wave function at time 0, I declare. Okay, so what is a minimum uncertainty wave packet? We've talked about a Gaussian, exactly. So the minimum uncertainty wave packet is a Gaussian. And suppose that I take my particle and I place it at time 0, x0, in a Gaussian. I'm going to properly normalize this Gaussian. I hate these factors of pi, but whatever. A root pi e to the minus x squared over 2a squared. Okay, so this is the wave function at time 0. I declare. I will just prepare the system in this state. And what I'm interested in knowing is, how does the system evolve in time? What is x, psi of x, and t? Okay, so how do we solve this problem? Well, we can just plug it into the Schrödinger equation directly and just by brute force try to crank it out. But the easier thing to do, I think we used all the way along. We're going to take a wave function, known dependence on x, expand it as a superposition of energy eigenstates. Each energy eigenstate evolves in a known fashion. We'll evolve those energy eigenstates in that superposition and do the sum again, resum it to get the evolution as a function of positions. Cool? Yeah.
So, given that this is given that the x basis or the e basis
Good. Here's the theorem. So the question is roughly, how do you know you can do that? How do you know you can expand the energy? And we have to go back to the spectral theorem, which tells us for any observable, the corresponding operator has a basis of eigenfunctions. Okay. So this is a theorem that I haven't proven, but that I'm telling you, and that we will use over and over and over again. Spectral theorem. What it tells you is that any operator has an eigenbasis. So if we find any good operator corresponding to an observable has a good eigenbasis. That means if we find the eigenfunctions of the energy operator, any state can be expanded as a superposition of that state. Okay. And the question of countable versus uncountable is a slightly subtle one. For example, how many points are there on the circle? Well, there's an uncountable number. How many momentum modes are there on the circle? Well, that's countable. How does that work? How do you describe that both in position and in momentum space? Come ask me afterwards. We'll talk about that more. But don't get too hung up on countable versus uncountable. It's not that big a difference. You're just summing. It's just what we sum over continuous or discrete thing. I'm being glib, but it's useful to be glib at that level. Okay, other questions before we. Okay, good. Yeah. Almost. So the question is, are we using the energy eigenstates because at the end of the day it's going to boil down to doing a Fourier transform because the energy eigenstates are just plain ways to EPIX? And that will be true, but that's not the reason we do it. It's a good question, so let me disentangle these. The point is that if I know that psi for any wave function in any system, if I know that psi of x is a zero-sum function, and I know the energy eigenstates of that system, then I can write this as sum over n of Cn phi n of x for some set of coefficients Cn, right? So that's the spectral theorem. Take an operator here, the energy, consider its eigenfunctions. They form a basis and these take to be expanded. But once we've expanded in the energy eigenbasis, right, specifically for the energy eigenbasis where E phi n is En phi n, then we know how these guys evolved in time. They evolved by E minus I En T upon H bar. And we also know that the Schrödinger equation is a linear equation, so we can superpose solutions and get a new solution. So now this is the expression for the full solution at time t. That's why we're using energy eigenstates. In this simple case of the free particle, it is a felicitous fact that the energy eigenstates are also Fourier modes. But that won't be true in general. For example, in the harmonic oscillator system, the harmonic oscillator energy eigenstates are Gaussians times some special functions, right? And we know how to compute that. That's why we use the raising lowering operators this way. But they're not plane waves. Nonetheless, despite not being Fourier modes, we can always expand an arbitrary function in the energy eigenbasis. And once we've done so, writing down the time evolution is straightforward. That answer your question? Yeah. Great. Anything else? Okay, so let's do it for this guy. So what are the energy eigenstates? There are these guys, and I'm just going to write it as e to the n so not assuming that k is positive. So k could be positive or negative, and the energy is e to the h squared k squared. And so we can write this as, we can write the wave function in this fashion, but we can also write it in Fourier transform form, which is integral dk upon root 2 pi, minus infinity to infinity. I'm mostly not going to write the bound, but we're going to minus infinity to infinity of, dk 1 over root 2 pi, e to the ikx, the plane wave, times the Fourier transform psi tilde of k. So here all I'm doing is defining for you the psi tilde. Well, if you actually computed this, so this is the Fourier transform, you actually computed this on, I think, the second problem set. So this is equal to the integral dk over root 2 pi e to the ikx. And I'm going to get the coefficients, I'm going to be careful about the coefficients, so root a over 4th root pi e to the minus k squared a squared over 2. So here, this is just to remind us, if we have a Gaussian with A, the Fourier transform is Gaussian with 1 upon A. So that's momentum and position uncertainty in Fourier space. Okay, and you did this in prop set 2. So this is an alternate way of writing this wave function for its Fourier transform. Ever cool that? Okay. But the nice thing about this is that we know how to time evolve this wave function. This tells us that psi of xt is equal to integral, and I'm going to get these coefficients all pulled out, integral of root a over root pi, integral dk upon root 2 pi, e to the I k. Minus omega t. And remember, omega depends on k, because it's k squared, h bar squared, k squared upon 2m divided by h squared. Times our Gaussian, e to the minus k squared, a squared upon 2. But, so everyone cool with that? So all I've done is I've taken this line, I pulled out the constant, and I've added the time evolution of the Fourier mode. So now we have this integral to give us the full, okay, so now we just have to do the integral. This is not so hard to do, but what makes it totally tractable is that if I just knew this was some function omega of k, I mean, that's complicated, I don't know how to do that integral, but I happen to know that E is h bar squared over h bar squared k squared upon 2m, which means that omega is equal to h bar k squared upon 2m. So I can rewrite this as minus h bar k squared upon 2m. Yes? That's a square root of a square root. No, that's okay. It's a horrible, horrible factor. So, okay, so what?
Okay, I miswrote that here. Yeah. Okay.
What do we take away from this? Well, this can be written in a nice form. Note that here we have a k squared, here we have a k squared, here we have a k. This is an integral over k, so this is still Gaussian. It's still the exponential of a quadratic function of k. So we can use our formulas for Gaussian integrals to do this integral. So to make that a little more obvious, let's simplify the form of this. So the form of this is again going to be square root of a over square root pi, integral dk on root 2 pi, e to the ikx. I'm going to take this term and group them together because they both have a k squared in the exponential, e to the minus k squared upon 2 times, now instead of just a squared, we have a squared plus I h bar upon 2m t. There's a typo in my notes. Crap. Good. So before we do anything else, let's just check dimensional analysis. This has units of 1 upon length squared. So this had better have units of length squared. That's a length squared. Good. This a length squared? So that's momentum times length, which is mass times length over time, divided by mass multiplied by time. So that's length squared. Good. So our units make sense. Sorry. This two we need. Oh, this one. Good. Thank you. Yes, thanks. Okay. Okay, so this is again a Gaussian. And look, before we knew we had a Gaussian, the Fourier transform is just this Gaussian. The only difference is it's now a Gaussian with width, not a, but a complex number. But if you go through the analysis of the Gaussian integral, that's perfectly fine.
So I'm just going to write what's happening here because this is a little complicated.
It's not a problem at all. The effective width is this.
So I don't think we haven't taken the Fourier transform yet. Hold on a second. I don't think we did that. What did we actually do here? So let me just see if I can walk through. All right. So we haven't done anything yet.
So what does that tell you about psi of t? So this tells you that psi of x of t is equal to root a over root pi. And now the width. So we have the 1 over root a, but now the effective width is this guy, a squared plus, okay, so it's square root of a squared plus I h bar upon m t e to the minus x squared over 4 a squared plus, whoops, where did my fork? There's a 2 there's a spurious 2 somewhere. I'm not sure where that 2 came from. There should be a 2 there. A squared plus I h bar upon m t. Okay. So at this point, it's not totally transparent to me what exactly this wave function is telling me, because there's still a phase downstairs in the width. So to get a little more intuition, let's look at something that's purely real. Let's look at the probability to find the particle at position x.
So I think what we did here is we
time t, that's just the norm squared of this guy. And if you go through a little bit of algebra, this is equal to 1 over root pi times, I'm going to write out 3 factors, times 1 over square root of, yes, good, a squared plus h bar upon 2ma squared t squared times e to the minus x squared upon 2 a squared plus h bar squared over 2ma squared. Oops, h bar over 2ma squared t. So what do we get?
All right, so this, I'm going to just see if I can answer. So this is a Gaussian. This is the width factor. And so what we're seeing, I think, is that this is going to like this. Oh, I think I should show that here. It's spreading out.
The probability distribution is again a Gaussian. But at any given moment in time, this should be t squared. At any given moment in time, the width is changing. The width of this Gaussian is changing in time. Notice this is purely real again. And meanwhile, the amplitude is also changing. And notice that it's changing in the following way. At time 0, this is the least it can possibly be. At time 0, this denominator is the least it can possibly be because that's gone. At any positive time, the denominator is larger, so the probability has dropped off. So the probability at any given point is decreasing. Except for, we also have this Gaussian whose width is increasing in time quadratically. It's getting wider and wider and wider. And you can check, so let's check dimensional analysis again. This should have units of length squared. And so this is momentum times length divided by mass. That's just a velocity. So this is a velocity squared times squared. That's good. So this has the correct units. So it's spreading with a velocity. V is equal to h bar upon 2ma. And what was A? A was the width at time 0. A was the minimum width. So graphically, let's draw this out. What is this telling us? Oh, and incidentally, a quick check. If this is supposed to be, it had better reproduce the correct answer at time 0. So what is this wave function at time 0? We lose that, and we recover the original wave function. So that's good. Okay. So graphically, what's going on? So let's plot P that's in T. At time 0, we have a Gaussian, and it's centered at 0. And it's got a width, which is just A. And this is at time t equals 0. At a subsequent time, it's again centered at x equals 0. Won't look that hard. But it's got a width, which is a squared, square root of a squared plus h bar upon 2ma squared t squared. So it's become shorter and wider such that it's still properly normalized. And at much later time, it will be a much lower and much broader Gaussian. Again, properly normalized, and again, centered at x equals 0. Is that cool? So what this says is if you start with your well-localized wave packet and you let go, it disperses. Does that make sense? Is that reasonable? How about this? What happens if you run the system backwards in time? If it's dispersing and getting wider, then intuitively you might expect that it'll get more sharp if you invade it back in time. In fact, what happens if you get negative in this analysis? It disperses again. right? It comes from being a very dispersed way to whack, to being very localized and whack, disperses out again. And notice that the sharper the wave function was localized, the smaller a was in the first place, the faster it disperses. This has a 1 upon a, has an a downstairs. So the more sharp it was at time 0, the faster it disperses away. This is what our analysis predicts. So let me give you 2 questions to think about. I'm not going to answer them right now. I want you to think about them. Not right. Well, think about them now, but also think about them more broadly as you do the problem set that you're reading for the readings for next week. So the width in this example was least at time t equals 0. Why? How could you build a wave function? How could you take this result and build a wave function whose width was minimum at some other time, say time t0? So that's one question. Second question, this wave function is sitting still. How do you make it move? And either the second or the third problem on the problem set is an introduction to that question. So here's a challenge to everyone. Construct a well-localized wave packet that's moving in the sense that it has a well-defined momentum expectation value. Okay. And again, look at your second or third problem on the problem set. And then repeat this entire analysis and check how the probability distribution evolves in time. And in particular, what I'd like you to do is verify that the probability distribution disperses, but simultaneously moves in the direction corresponding to the initial momentum with that momentum. The center of the wave packet moves according to the momentum that you gave it in the first place. It's a free particle, so should the expectation value of the momentum change over time? No. And indeed it won't. So that's a challenge for you. Okay, questions at this point? Yeah? Yes. Sorry, this is at x is equal to 0? Good. So what I'm plotting, so I'm plotting p of x and t as a function of x for different times. So this is time 0. This was time t equals something, not 0, t equals 1. This is some time t equals large. Right. Good. So if x is 0, then the Gaussian contribution is always giving me 1. But there's still this amplitude. And the amplitude is the denominator getting larger and larger with time. So indeed, the amplitude should be falling off. Is that? Yeah, absolutely. Because the width, so what the width is saying, look, how rapidly as we increase x, how rapidly does this fall off as a Gaussian? And so if time is increasing, if time is very, very large, then this denominator is huge. So in order for this Gaussian to suppress the wave function, x has to be very, very large. But remember, so this x is not the position of the particle. X is the position at which we're valuing the probability. So what we're plotting is we're probably good. Yeah, this is an easy thing to consider. What is this quantity telling us? This quantity is telling us the probability that the probability density that we find the particle at position x at time t. So x is like, look, where do you want to look? And you tell me the x, and I tell you how likely it is to be found there. So what this is telling us is that the probability distribution to find the particle starts out sharply peak, then it becomes more and more dispersed. So at the initial time, how likely am I to find the particle, say, here? Not at all. But at a very late time, who knows? It could be there. But I mean, my confidence is very, very limited because the probability distribution is very wide. Did that answer your question? Great. Yeah. Excellent question. So that's a fantastic question. So we talked about measurements of position. We talked about measurement. So after you measure an observable, the system is left in an eigenstate of the observable corresponding to the observed eigenvalue. So suppose I measure, I have some potential, or I have some particle, and it's moving around, but it's in some complicated wave function, it's in some complicated state, and I measure its position to be here. But my measurement isn't perfect. I know it's here with some reasonable confidence, with some reasonable width, right? What's going to be the state thereafter? Well, it's going to be a state corresponding to being more or less here with some uncertainty. Oh, look, there's that state. And what happens subsequently? What happens subsequently is my probability immediately decreases. And this is exactly what we saw before. Thank you for asking this question. It's a very good question. This is exactly what we saw before. If we make an arbitrarily precise measurement of the position, what would be the width? Yeah, I mean, delta, so the width would be 0. That little a would be 0. So how rapidly does it disperse? Pretty fast, right? And you have to worry a little bit because that's getting a little relativistic. So, yeah. Yeah, so, okay, that's a good question. So, so you make a measurement, it's not perfect, there's some uncertainty. And so let me rephrase this question slightly. So here's another version of this question. Suppose I make a measurement of a system. If there are 2 possible configurations, 2 possible states, and I measure an eigenvalue corresponding to one of them, then I know what state the system is in, right? Then if I'm measuring something like position, where I'm inescapably going to be measuring that position with some uncertainty, what state is left in afterwards? Do I know what state is left in afterwards? No, I know approximately what state. It's going to be a state corresponding. Okay, so then I have to have some model for the probability distribution of being in state. But usually what we'll do is we'll say we'll approximate that. We'll model that unknown. We don't know exactly what state it is. We don't know exactly what position we measure. We'll model that by saying, look, by law of large numbers, it's going to be roughly a Gaussian centered around the position with the width, which is our expected uncertainty. Now, it depends on exactly what measurement you're doing. Sometimes that's not the right thing to do, but that's sort of maximally not okay. This is an interesting but complicated question, so I'm asking you off this question. Yeah. Yeah, exactly. So what is this velocity? So this velocity, what's it telling us? It's telling us how rapidly the wave spreads out. Right? So does that indicate anything moving? No. What's the expected value of the position at any time? 0, because this is an even function, right? What's the position? Well, it's just like to be here is here. It's just that the probability of being here gets greater and greater over time for a while. Yeah, one last question. Yeah. Yeah, okay, so the question is, can you talk a little bit more about why the behavior as time increases is the same as the behavior as time, as we go backwards in time? And I'm not sure how best to answer that, but let me give it a go. So the first thing is to say, look at our solution, okay, and look at the probability distribution. Probability distribution is completely even in time, right? Depends only on t squared. So I ask what happens at time t, it's the same as what happened at time minus t. That's interesting in a slightly unusual situation. Let's look back at the wave function. Is that true of the wave function? No, because the phase and the complex parts depend on, okay, so the amplitude doesn't depend on whether it's t or minus t, but the phase does, and that's a useful clue. But now here's a better way. What was the weird thing that made this t reversal invariant? There's another weird property of this, which is that set it at 0, it's sitting still. If we give it momentum, that would also not have been true. So the best answer I can give you, though, requires knowing what happens when you have a finite momentum. So let me just sketch quickly. So when we have a momentum, how do we take this wave packet and give it momentum k sub k naught? So this is probably in your problem set, but I will answer it for you. Okay. You multiply by phase e to the I k naught x. Okay. And the expectation value will now shift to be h bar k naught for a minute. Okay. So what's that going to do for us? Well, if we do the Fourier transform, that's going to shift k to k minus k naught. And so we can repeat the entire analysis and get roughly k naught here. The important thing is we're going to end up with we end up with phases. So the way to read off time 0 is going to be, well, many answers to this. As time increases or decreases, we'll see from this phase that the entire wave packet is going to continue moving, it's going to continue walking across. And that breaks the t minus t invariance, because at minus t it would have been over here. And then think about that first question. How would you make it become minimum wave packet at some time which is not time equals 0? So when you have answers to both of those, you'll have the answer to your question. Yeah?
And we say the probability was about 5 seconds here.
Right.
So you have to be aware of the
Good. So that's not exactly what the probability distribution is like. So what the probability distribution is telling you is not what happens when you make a measurement. It's given this state, what would happen. And so when you ask about the probability distribution at time minus 7, what you're saying is, given the wave function now, what must the wave function have been at time earlier? Such that Schrödinger revolution, not measurement, but Schrödinger revolution gives you this. And so what that's telling you is someone earlier been around to do that experiment, would value that they have gone. Absolutely, if they had done the measurement. Right. There's a difference between knowing what probability distribution would be if you were to do a measurement and actually doing the measurement and changing the wave function. Merely speaking about what the wave function was earlier. No one's done any measurements, exactly. Right now, the probability distribution does not do a measurement. Exactly. It's one last question, sorry. Yeah. Well, you can ask the question slightly differently. If you had wanted to compare the state at time minus 7, such that you got this state at time 0, right? This is the inverse of asking, given that the state at here now is going to be at time 7. Right? So they're completely reasonable questions. What should you have done last week so that you get a problem today? There was no problem to do today. Just okay. So with that said, we've done an analytic analysis. We've done a quick computation that showed analytically that showed analytically what happens to a Gaussian wave packet. However, here's what it is. Good. So we've done an analysis that wave function evolves over time. What I'd like to do now is use some of the FET simulations to see this effect, and also to predict similar effects. So what do you think about this as? So this is the FET quantum wave packet simulation. You haven't played with these. You totally should. They're fantastic. They're very good developing the equation. All props to the Colorado group. They're excellent. So what I'm going to do is run through a series of experiments that we couldn't in principle do on tabletop, although it would be fabulously difficult. But the basic physics is simple. And second, run it on the computer on the tabletop because it's easier and cheaper. But I'm going to take these as experiments that we're actually running. So here, what these diagrams show, for those of you who haven't played with this is the potential that I'm going to be working with. The green, the position tells me the actual value of the energy of my wave packet, and the width tells me how broad that wave packet is. And roughly speaking, how green it is tells me how much support I have on that particular energy eigenstate. And I can change that by tuning the initial width of the wave packet. So if I make the width very wide, if I make the width very narrow, I need lots and lots of different energy eigenstates to make a narrow, well-localized wave packet. And if I allow the wave packet to be quite wide, then I don't need as many energy eigenstates. So let me make that a little more obvious. So fewer energy eigenstates are needed to have a thinner band in energy, more energy eigenstates are needed to have a more wide band. Is that cool then? And what this program does is it just integrates the Schrödinger equation. It just integrates the Schrödinger equation. So what I want to do is I want to quickly, okay, so this is the wave function, its absolute value, and this is the probability density, the norm squared. And so let's see what happens. So what is this initial state? This initial state, in fact, I'm going to reload the configuration. So this initial state corresponds to being more or less here with some uncertainty. So that's our side back to 0. And let's see how this evolves. So first, before I actually have involved, what do you think is going to happen? And remember, it's got some initial momentum as well. Okay, so there it is evolving, and it's continuing to evolve. It's really quite boring. This is a free particle. Wow, that was dull. Okay, so let's try that again. Let's look also at the real part and look what the phase of the wave function is doing. That's a cheat. So here, there's something really cool going on. It might not be obvious, but look back at this. Look at how rapidly the wave packet moves and how rapidly the phase moves. Which one's moving faster? Yeah, the wave packet. And the wave packet, it's kind of hard to tell exactly how much faster it's moving, but we can get that from this. What's the velocity of a single plane wave, the phase velocity? So the phase velocity for problem set 1 is h bar squared is h bar k squared upon 2m omega. Let's see what this says. Omega upon k, which is just equal to h bar k upon 2m. But that's bad because that's the momentum. Divide the momentum by the mass. That's the classical velocity. So this says that the phase of any plane wave is moving with half the classical velocity. That's weird. On the other hand, the group velocity of a wave packet, a normalizable wave packet, is d omega dk. And d omega dk will pull it down an extra factor of 2. This is equal to h bar k upon m. This is the classical velocity. So this is the difference between the phase and the group velocity. And that's exactly what we're seeing here. So the first thing to notice is you see the difference between the phase and the group velocity. So that's good. That should be reassuring. But there's something else that's really quite nice about this. Let's make the wave packet really very narrow. Okay. So here's much more narrow, and let's let the system evolve. And now you can see that the probability density is falling off quite rapidly. Right? Let's see that again. Cool. The probability distribution is falling off very rapidly. And there's also a kind of cool thing that's happening is you're seeing an accumulation of phase up here and a diminution down here. We can make that a little more sharp. Oops. Sorry. Oops. Yeah. So that is a combination of good things and the code being slightly badly behaved. But, right. So the more narrow I make that initial so I made that really narrow, and how rapidly does it fall off? Okay, so that very narrow wave packet by time 10 is like at a quarter. But if we made it much wider, that very narrow wave packet started out much lower, and it stays roughly the same height. It's just diminishing very, very slowly. And that's just the 1 over A effect. Okay, so this is nice. And I guess the way I like to think about this is confirming rather nicely our predictions. Okay, so now I want to take a slightly different system. So
I do drink coffee, but I'm just drinking water right now.
We all know what's going to happen. Here's a hill. And you know, if this were the real world, I would think this
is speed up.
That's a nice finite fall off. You know, the sort of place you don't want to go skiing off. So, well, I don't. So imagine you take an object of mass m and you let it slide along in this potential. What will happen? It will move along at some velocity. It will get to this cliff. It will fall to the cliff and end up going much faster at the bottom. Yeah. So if you kick it here, it will get over there and it will end up much faster. What happens to this wave packet? So we're solving the Schrödinger equation. It's exactly the same thing we've done before. Let's solve it. So here's our initial wave packet, nice and well localized. There's our wave function. And what happens? Ooh. So at that point, something interesting has happened. You see that, for the most part, most of the probabilities are here, but not all the probabilities are here. There's still a tiny probability that the particle stays near the wall for a while. Let's watch what happens to that probability time that. And now you should notice that it's decayed into a wave packet that's over here, and then a superposition of a wave packet over here moving to the left. This wave has scattered off the barrier going downhill, mostly transmitted, but some of it reflected, which is kind of spooky. So let's watch that. I'm going to make this much more extreme. Okay, so here's a much more extreme version of this. I'm going to make the energy very close to the height of the potential. So the energy is very, very close to the height of the potential, and the potential is far away. We're still reasonably low. I'm going to make it a little less localized just to really crank up the suspense. Okay. So watch what happens now. So first off, what do you expect to happen? So we made the energy of the wave packet just barely higher than the energy of the hill. So it's almost classically disallowed from being up here. What does that mean about its velocity, its effective velocity? Yeah, the momentum, the expectative value for the momentum should be very low, because it just has a little bit of spare energy. So the expected value for the momentum should be very low. It should dribble until it gets to the cliff, and then go flying off. So let's see if that's what we see. So it's dribbling. But look at the probability density down here. Oh, indeed, we do see little waves, and those waves are moving off really fast. But the amplitude is exceedingly small. Instead, what we're seeing is a huge pilot of probability just before the wall. Similar to what we saw a minute ago, except the probability is much, much larger. And what's going to happen now? It's leaking. It's definitely leaking. But an awful lot of the probability density is not going off the cliff. This would be like Thelma and Louise, like cruising off the cliff and then like just not falling. This is a very disconcerting. You guys too, yeah. Okay, so see what happened. See what happened here. We've got this nice big amplitude to go across. Let's go back. You really want to fall down classically. Quantum mechanically, you can't. It's impossible. So in fact, the probability to reflect back is 41. We're going to see how to calculate that in the next few lectures. Yeah. Transition was reasonably high. Yeah. It wasn't really. Sorry. Yeah, it wasn't apparent. The way it was apparent was just the fact that the amplitude that bounced back was relatively small. So what was going on is any little bit of probability that fell down had a large effective momentum, just ran off the screen very rapidly. So it's hard to see that in the simulation. It's true. Okay, we can make the squeeze and tune. There we go. So here's, yeah, that's about as good as I'm going to get. And it's just going to be glacially slow. Okay. So this is just going to be preposterously slow. I'm not even sure there's much point in. But you can see what's going to happen. It's going to build up. We're going to get a little leak off. But for the most part, the way back is going to go back to the left. Okay. Questions about this one before we move on to the next? Yeah. Yeah, exactly. So R and T here are going to be defined as the probability that this wave packet gets off to infinity in either direction. Yeah. Then you can't have a wave packet on the left that's moving, right? because you remember that the wave packet, in order to have an expected momentum, needs to be oscillating. But if the energy is lower, the potential is exponential. So the expectation of momentum is zero. So you can't have a particle moving to the left because it's got energy less than the height of the barrier. Cool. Yeah. The green thing is the energy of the wave packet that I'm sending in. Okay, so let's go to the next one. So this is something we'd like to understand. This is the reason I'm showing this is I want to explain this. I want to explain this phenomena as well as we already did dispersion. I want to explain this phenomena they reflect when going downhill, which is perhaps surprising. And I want to ask how efficiently you reflect off any given barrier. Yeah, question. Oh yeah, absolutely. So suppose I have a little capacitor plate. Okay, so and there's a potential difference across it and a hole, so a particle could shoot through it. So I mean, it doesn't have to be insanely small, but a hole.
Usually just in the morning.
Here to the other side of the capacitor plate, it will have accelerated across the potential difference. So if you think about the effective potential energy, the potential is decreasing linearly. It's a constant electric field. So over this short domain between the capacitor plates, we have effectively a linear potential energy. Yeah. So I have a particle that I send with very low momentum by increasing charge. It gets to the capacitor plate, and if it goes through the capacitor plate, it ends with a lot more energy relative to potential energy. Okay, cool. So a little capacitor plate with a hole in it is a beautiful example of this system. And making it infinitely sharp, well, that would require me to, but making it very sharp is no problem. Okay, so here's the inverse of what we just did, which is sending a particle into a barrier. And so there you see, it does some quite awesome things. And I want to pause it right here. This is the energy band. So we have the green represents, it says that at any given energy inside this green band, there's some contribution from the corresponding energy I can state toward wave packet. There isn't any contribution from states up here where there's no green, which means that all the contributions come from energy I can state with energy below the height of the barrier. None of them have enough energy to cross the barrier. And what we see when we send in our wave packet is some complicated mucking around near the barrier, but in particular, right there, there's a finite, non-zero probability that you're found in the classically disallowed region, in the region where you didn't have enough energy to get there. Right, we see right there. And meanwhile, there's also a huge pile up here. This is a hard wall. Normally, classically, from a hard wall, you roll along, you hit a hard wall, and you bounce off instantaneously with the same velocity. But here, what we're saying is, no, you're not just the wave doesn't just exactly bounce off instantaneously. We get this complicated piling up and interference effect. So what's going on there? Well, it's precisely an interference effect. So look at the wave function. The wave function is a much easier thing to look at. So the red is the amplitude. Or sorry, the red is the real part. The black is the phase. So the real part is actually behaving quite reasonably. It looks like it's just bouncing right off. But the physical thing is the probability distribution. The probability distribution has interference terms from the various different contributions to the wave function. So at the collision, those interference effects are very important. And at late times, notice what's happened. At late times, the probability distribution all went right back off. So that's something else we'd like to understand. Penetration into the barrier from classically disallowed wave packet. Yeah. Yeah, the wave packet, exactly. So the wave packet is always going to expand. And the reason is, we're taking a wave packet which is a reasonably well-placed, approximately Gaussian wave packet. So whatever else is going on, while it's in the part of the potential where the potential is constant, it also just dispersing. Right? And so we can see that here. Let's make that more obvious. Let's make the wave packet, the initial wave packet, much more narrow. Okay, so the wave packet is much more narrow. We're going to watch it disperse, and let's make the wall move the wall over here. So long before it hits the wall, it's going to disperse, right? That's what we expect. And look, watch it disperse. Okay, now it gets to the wall. And yeah, sort of a mess. Now you see that there's contributions to the wave function over here. There's support for the wave function moving off to the right. But now notice that we have support on energy I can state with energy above the barrier. So indeed it was possible for some contribution to go up to the right. Okay. So one more of these guys. Oh, I guess two more. These are fun. So here's a hard wall. Let's take the right. So here's a hard wall, but it's a finite width. It's a finite width barrier. And what happens? Well, this is basically the same as what we just saw. We collided against that first wall, and since there's an exponential fall off, it doesn't really matter that there's this other wall where it falls down here because the wave function is just exponentially suppressed in the classically disallowed region. So let's see that again. It's always going to be exponentially suppressed in the classically disallowed region. Let's see, there's that big exponential suppression. So there's some funny probability find part here. You're really unlikely to find it out here exponentially. On the other hand, if we make the barrier, so let's think about this barrier. Classically, this is just as good as a thick barrier. You can't get past this wall. But quantum what happens? You go right through, right? Just right on. Yeah. Right through. It barely even changes shape. It barely even changes shape. Just goes right on through. Now there's some probability that you go off to the left, that you bounce off. I share your pain. I totally do. So I'd like to do another experiment which demonstrates the difference between classical and quantum mechanical physics. Right? So we have to explain to you, and this is going to turn out being, this is not a hard thing to explain. Especially this version, this is going to be not so hard to explain. Okay, the next one, this is, yeah, question. It does absolutely. So the height of the spike and the width of the spike matter. Let's make it a little wider. And what we're going to see now is that it's a little less likely to go through. If we make it just tiny bit wider, we'll see that it's much less likely. We'll see much stronger reflect width. So both the height and the width are going to turn out to matter. And so here you can see that there's an appreciable reflection, which there wasn't previously. Let's make it just a little bit wider. And now it's an awful lot closer to half and half. See the bottom two lumps. Let's make it just ever so slightly wider. And again, looking up here, we're going to have a transmitted bit, we're also going to have reflected. Now it looks like the reflected bit is even a little bit larger maybe, and we can actually compute reflection transmission here. 72% gets reflected and 28% gets transmitted. I really strongly encourage you to do these simulations. They're both fun and very illuminating. Yeah?
So if what happens the higher got, the less got transmitted?
Yes.
So this where a delta function would end.
Well, what's the width? So what happens when we have what happens when we make the well less and less thin, or more and more thin? The more it gets through, so we've got a competition between the height and the width. So one of the problems on your problem set, either this week or next week, you can recall, will be for the delta function barrier, compute the transmission probability. Okay. And in fact, we're going to ask you to compute the transmission probability through two delta functions. And in fact, that's this week. And then next week, we're going to show you a sneaky way using something called the matrix to construct bound states for those guys. Anyway, okay. So next, the last simulation today. So this is the inverse of what we just did. Instead of having a potential barrier, we have a potential well. Yeah. So what do you expect to happen? Well, there's a wave packet, and it comes along, and all heck breaks loose inside. We get some excitations, and it tunnels across. But we see there's all this sort of wiggling around inside the wave packet, and we get some support going off to the right, some support going off to the left. That's good. But nothing sticks around inside. It looks like there is, but it's going to slowly decay away as it goes up to the boundary. These are scattering states. So one way to think about what's going on here is it first scatters downhill, and then it scatters uphill. But there's a very funny thing that happens when you can scatter uphill and scatter downhill. As we saw, if you have scattering uphill, and there's some probability that you reflect, and some probability that you transmit. And when you scatter uphill, there's some probability you transmit and some probability that you reflect. But if you have both an uphill and a downhill, when you have a well, something amazing happens. Consider this well. This didn't work very well. Let's take a much larger. So at some point, I think it was last year, some student's cell phone went off. And I was like, oh, come on, dude. You can't do that. And like 5 minutes later, my cell phone went off. So I feel you think, please learn that again. Okay, so let's. Okay, so here we go. So this is a very similar system. Let's take this one with a different wave packet and slightly different width. And what happens? Well, all this wave packet just sort of goes on. But how much probability is going back off to the left? Very little. In fact, we can really work this. Oh, sorry, I need this, otherwise I'm very bad at this. There's some probability that reflects from the first well. There's some probability that reflects from the second well. But the probability that reflects from the combination of the two? 0. How can that be? So this is just like the boxes at the very beginning. There's some probability. So to go in the system, so let's go back to the beginning. There's some amplitude to go from the left side to the right-hand side by going, so how would you go from the left-hand side to the right-hand side? You go across, you transmit, and then transmit, right? So it's the transmission probability, transmission amplitude, and transmission amplitude is the product. But is that the only thing that can happen? What are other possible things that can happen? Yeah, you could transmit, reflect, transmit. You can also transmit, reflect, transmit. And you do that an arbitrary number of times. And each of those contributions is a contribution to the amplitude. And when you compute the probability to transmit, you don't take the square of some of the probabilities, you take the square of the sum of the amplitudes. And what we will find, when we'll do this next time, when we actually do this calculation, is that interference effect, from taking the square of the sum of the amplitudes from each of the possible bouncings, can interfere destructively and it can interfere constructively. We can find points when the reflection is extremely low. We can find points where the transmission is perfect. Yeah.
So 2 questions. One, if it says that the reflecting coefficient is 0, why did it look like there was a wave packet?
Yeah, excellent question. So, and indeed, there is a little bit here. So now I have to tell you a little bit about how the computers calculate this reflection amplitude. The way it's doing that is it's saying, suppose I have a state which has a definite energy at the center of this distribution. Then the corresponding reflection amplitude would be 0. But in fact, I have a superposition of taking a superposition of them. And so the contributions from slightly different energies are giving me some small reflection.
Also, why
Yeah, that's really, let me rephrase that question. The question is why do you have to find the width of that well? Let me ask the question slightly differently. How does the reflection probability depend on the width of the well? What's going on at these special values of the energy or special values of the width of the well when the transmission is perfect? Which I will call you, is that happening? And we'll see that. Okay, so that's the question I want you guys to have. So I'm done on the experiments. You guys should play with these. No, I'm fine. To get intuition yet. It's a class, so excellent. Sure. So here's what I'm going to tell you. I'm going to tell you 2 things. First off, if I take a classical particle and put it through these potentials, for example, this potential. Okay. If I take a classical particle and put it in this potential, it's got an energy here. Does it ever reflect back? No. Always it rolls and continues on. Always. Okay. So if I take a quantum particle and I do this, will it reflect back? Apparently sometimes. Okay. Now, how do I encode that? I encode that in studying solutions to the wave equation. Dt minus, or sorry, IH bar. Dt of psi is equal to minus h bar squared upon 2m dx squared psi plus v psi. Right? So this property of the quantum particle that it reflects is a property of solutions to this equation when I interpret the amplitude squared as probability. But this equation doesn't just govern, this isn't the only place this equation has ever shown up. An equation at least very similar to this shows up in studying the propagation of waves on a string, for example, where the potential is played by the role of the tension or the density of the string. So as you have a wave coming along the string, as I'm sure you did in -3, you have a wave coming along the string, and then the thickness or density of the string changes, becomes thicker or thinner, then sometimes you have reflections off that interface from impedance dimensional wave reason. And as you move across the other side, you get reflections again. And the thing that matters is not the amplitude of the amplitude. One of the things that matters is not the amplitude, but it's the intensity. The intensity is the square. And so you get interference effects. So indeed, this phenomenon of reflection and multiple reflection shows up in certain classical systems, but it shows up not in classical particle systems. It shows up in classical wave systems, like waves on a chain or waves in a rope. And they're governed by effectively the same equations, not exactly, but effectively the same equations as the Schrödinger evolution governs the wave function. But the difference is that those classical fields, those classical continuous objects, have waves on them, but those waves are actual waves, right? You see the rope is everywhere. In the case of the quantum mechanical description of a particle, the particle could be anywhere, but it is a particle, it is a chunk, it is a thing, and this wave is a probability wave in our knowledge, our command of the system. Other questions? Okay, so let's do the first example of this kind of system. So let's do the very first example we talked about apart from the free particle, which is the potential step. Example is the potential step. Okay, and what we want to do is we want to find the eigenfunctions of the following potential: constant, barrier, constant. And then they call the height here V naught and the height here 0, and I'll call this position x equals 0. And I want to send in a wave. I want to send in, I want to think about the physics of sending in a particle that has an energy E naught. Okay. Now to think about the dynamics, before we think about the time evolution of a localized wave packet, as we saw in the free particle, it behooves us to find the energy eigenstates. Then we can deduce the evolution of the wave packet by doing resummation. Yeah? Using the superposition principle. So let's first find the energy eigenstates. In fact, this will turn out to encode all the information we need. So we want to find phi E of x. What is the energy eigenfunction with energy E, let's say? And we know the answer on this side, and we know the answer on this side because it's just constant, that's a free particle, and we know how to write the solution. So we can write this as, this is equal to, on the left-hand side, it's just a sum of plane waves, it's exactly that form, A e to the I kx, plus B e to the minus I kx. On the left, and on the right, we have C e to the minus I alpha x. Oh, sorry. On this side, it's disallowed, right? Classically disallowed. So this is e to the minus alpha. Oh, sorry, you want to, yeah, e to the plus alpha x plus b e to the minus alpha x, where h bar squared k squared on 2m is equal to e, and h bar squared alpha squared upon 2m is equal to V naught minus E, right? The positive quantity. Okay, so we need to satisfy our various continuity and normalizability conditions, and in particular, what had the wave function better do out this way? It had better not divert. Are we going to be able to build normalizable wave packets out of it? Or are we going to be able to find normalizable wave functions of this form? No, because there are always going to be plane waves on the left. So the best we'll be able to do is find delta function normalizable energy eigenstates. That's not such a big deal because we can build wave packets as we discussed before. Yeah? Okay, but on the other hand, it's one thing to be delta function normalizable, going to just a wave. It's another thing to diverge. So if we want to build something that's normalizable up to a delta function normalization condition, this had better vanish. Yeah? But on top of that, we need that the wave function is continuous. So at x equals 0, we need that phi and phi prime are continuous. So that turns out to be an easy set of equations. So for phi, this says that a plus b is equal to d. And for phi prime, this says that ik, a, and then the next one is going to give me minus ik, a minus b, is equal to, on the right-hand side, minus alpha c. Because the exponentials all evaluate to 0. So we can invert these to get that d is equal to 2, that's weird. Oh, sorry, d. Thank you. To invert those to get the 2k over k plus I alpha, I think. Yes, k plus I alpha. And b is equal to k minus I alpha over k plus I alpha. Okay. And so you can plug these back in and get the explicit form of the wave function. And this is, now what condition must the energy satisfy in order that this is a solution that's continuous and smooth and its derivative is continuous? Last time we found that in order to satisfy for the finite well continuity conditions, only certain values of the energy were allowed. Here we impose normalizability and continuity. What's the condition on the energy?
Nothing.
This is a trick question. There isn't any, right? There's no, for any energy we can find a solution. There was no consistency condition amongst these. Any energy. So are the energy values continuous or discrete? Continuous. Anything above zero energy is allowed for the system is continuous. So what does this wave function look like? Oh, I really should have done this. What does this wave function look like? Well, it's oscillating up here. And it's decaying in here. And it's smooth. So what's the meaning of this? What's the physical meaning? Well, here's the way I want to interpret this. How does this system evolve in time? How does this wave function evolve in time? So this is psi of x, psi of x. What's psi of x and t?
It's the same.
Well, it just gets hit by an e to the minus I omega t.
No, you get minus.
Omega t
Plus the phase.
omega t minus I omega t. Everyone cool with that? So all I did is I just said that this is an energy eigenfunction and frequency omega is equal to e upon h bar. And saying that this is an energetic state tells you that under time evolution, it evolves by rotation by an overall phase, e minus I omega t. And then I just multiplied the whole thing by e minus I omega t and distributed it. So here's the minus I omega t, minus I omega t, minus I omega t phase. So doing that, though, gives us a simple interpretation compared to our free particle. Eating out kx minus omega t, it's wave moving to the right with velocity omega over k, phase velocity. This is a right moving contribution, this is a plus. And this is a left moving contribution. Can we call that? So on the left-hand side, what we have is a superposition of a wave moving to the right and a wave moving to the left. Yeah? On the right, what do we have? We have an exponentially falling function whose phase rotates. Is this a traveling wave? No, it doesn't have any crests. It just has an overall phase that rotates. And now here's one key thing. If we look at this, what's B? We did the calculation of B. B is k minus I alpha over k plus I alpha. What's the norm squared of B? Well, the norm squared of B is going to be multiply this by its complex conjugate and multiply this by its complex conjugate, but they're each other's complex conjugates. They'll cancel. The norm squared is 1. It's a pure phase. So this tells you B is a pure phase. Yeah. So now look back at this. If B is a pure phase, if B is a pure phase, then this left moving piece has the same amplitude as the right moving piece. This is a standing wave. All it's doing is it's rotating by an overall phase, but it's a standing wave because it's a superposition of a wave moving this way and a wave moving that way with the same amplitude, just slightly shifted. So the fact that there's a little shift tells you that its norm squared is not constant, it has a small wave. So what we see is we get a standing wave that matches nicely onto a decaying exponential in this cloud. So what that tells you is, what's the probability to get arbitrarily far to the right?
Decaying.
0, right? It's exponentially suppressed. What's the probability that you found something on the left? Well, it's the norm squared of that, which is some standing wave.
Mm-hmm.
So the reflection, how good is this as a mirror? It's a perfect mirror. Well, it's not. Now we have to quibble about what we mean by a perfect mirror. It reflects with a phase. Right? It reflects with a phase beta. I'm going to call that phase. I'm going to pick conventions here because they're consistent throughout. Let's call that e to the I phi. Okay. So it reflects with a phase phi, which is to say the norm squared is 1. And what happens? I don't want to do this. So In what situation would you expect this to be a truly perfect mirror? This potential. When do you expect reflection to be truly perfect? Yeah, exactly. So if the height here were infinitely high, then there's no probability, you can't leak in at all. There's no exponential tail. It's just zero. So in the case that V0 is much greater than E, what do we get? We get that V0 is much greater than E. That means alpha is gigantic and K is very, very small. If alpha is gigantic and K is very small, negligibly small, times alpha over I alpha, this just becomes -1, the element. So in the limit that the wall is really truly hard wall, this phase becomes -1. What happens to a wave when it bounces off a perfect mirror? Its phase is inverted exactly. Here we see that the phase shift is pi. You get a -1 precisely when the barrier is infinitely high. When the barrier is a finite height, classically would be a perfect mirror still, but quantum mechanically it's no longer a perfect mirror. There's a phase shift, which indicates that the wave is extending a little bit into the material. The wave is extending a little bit into the classically distal average. This phase shift, called the scattering phase shift, is going to play a huge role for us. It goes an enormous amount of physics, as we'll see over the next few weeks. And at the end of the semester, it'll be important for us in our discussion of bands and solids. So, at this point, though, we've got... I'm going to be using phrases like, this is the part of the wave function moving to the right, and that's the part of the wave function moving to the left. I'm going to say the wave function is a superposition of those two things. But I need a more precise version of stuff is going to the right. And this is where the probability density, rho squared, psi squared, and the probability current, which you guys have constructed in
Concept 5.
on the problem set, which is h bar upon 2mi, sine right psi star, dx psi, minus, oops, psi dx psi star. These guys satisfy the conservation equation, which is d rho dt, the time rate of change of the density at some particular point, at time t, is equal to minus the gradient, derivative with respect to x, of j. And I should really call this jx. It's the current in the x direction. So this is a conservation equation. Just like for the conservation of charge, and you guys should have all effectively derived this on the problem set. Yeah. Is the I, this, oh, sorry, the I is below. That's just my horrible handwriting. So, what I want to define very quickly is I want to be able to come up with an unambiguous definition of how much stuff is going left and how much stuff is going right. And the way I'm going to do that is I'm going to say that the wave function, in general, do that here. When we have a wave function at some point, it can be approximated, if the potential is roughly constant at that point, it can be approximated the following way. The wave function is going to be psi is equal to psi incident plus psi transmitted, or psi, psi reflected, on the left of my barrier, and psi transmitted on the right. Where psi incident is that right moving part, the part that's moving towards the barrier. Psi reflected is the left moving part that's reflected. Psi transmitted is the part that is on the right-hand side of the entire thing. So here the idea is I'm sending in something from the left, it can either reflect or it can transmit. So this is just my notation for these guys. And so what I want is a measure of how much stuff is moving, going left, how much stuff is going right. And the way to do that is to use the probability current and to say that associated to the incident term in the wave function is an incident current, which is h bar k upon m from a squared. So if we take this wave function, take that expression, plug it into j, this is what you get. If you take the reflected part, b e to the minus I kx minus omega t, and you plug it into the current expression, you get the part of, sorry, I should call it capital J, you get the part of the current corresponding to the reflected term, which is h bar k with a minus k upon m b squared. And we'll get the j transmitted is 0, something that you proved in your problem set. If the wave function is real, it must, the current is 0. So let's think about what this is telling us quickly. So what is this pointing? So what is a current? Current is the amount of stuff moving per unit time. Right? It's the charge times the velocity. So what's the stuff we're interested in? It's the probability density. There's a squared, norm a squared. That's the probability amplitude or probability density of the right moving piece. And it's just considered in isolation. So that's the probability density, the amount of stuff. And this is the momentum of that wave. That's e to the I kx. There's h bar k, that's the momentum divided by the mass, which is the classical velocity. The amount of stuff times the velocity, that's a current. It's the current with which velocity, with which probability is flowing across a point. Similarly, JR, that's the amount of stuff, and the velocity is minus h bar k upon m. So again, the current is the amount of stuff times the velocity. I'm going to define, this is just a definition, it's a reasonable choice of definition. The transmission probability is the ratio, the norm squared of J transmitted over J incident. And here's why this is the reasonable thing, incident. Here's why this is the reasonable quantity. This is saying how much current is moving in from the left, right? How much stuff is moving in, and how much stuff is moving off on the right, to the right. So what is this in this case? 0. Okay, although this is a general definition. And similarly, the reflection, you can either write as 1 minus the transmission, because either you transmit or you reflect. The probability must sum to 1. Or you can write R as the current reflected. What fraction of the incident current is in fact reflected? And here this is 1, because beta B is a phase, and the norm squared of a phase is 1. Okay. So on your problem set, you'll be going through the computation of various reflection and transmission amplitudes for this potential, and we'll pick up on this with the barrier uphill next week.
So I got a question about coffee while I was working on this lecture. I didn't have time to answer. Yeah, I drink coffee in the morning. Generally, I know it's not feasible for all people, but I recommend if you're feeling really tired, taking short naps. And the reason a short nap is better than coffee is because what coffee does is it blocks the receptors in your brain that make you feel sleepy, but that wears off, and you haven't removed those chemicals in your body. You haven't gotten any sleep. So you feel even more tired once it wears off. So coffee is good. I like coffee, so I'm not against drinking coffee, but it's no real substitute for sleep. And it can help a little bit with performance. Caffeine can help a little bit. So if you know you need to concentrate, some coffee is probably good. But if you're feeling tired around noon, I'm a big fan of the 20-minute nap. I took one before I started doing this lecture, and it helps you feel refreshed because compared to coffee, which just suppresses the receptors, taking a short nap actually clears those up so you can focus a little better. It's not the same as sleeping all night, and I think sleeping well at night is a good step too. But yeah, I like drinking coffee though. I like drinking it in the morning, but definitely you can drink too much coffee. All right, so we've done this was lecture 12, so let's do lecture 13. I'm probably not going to finish this today, so we'll just go as far as we can. Maybe get done a chunk of it and pick it up in the morning.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare. This is free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Any questions from last lecture from before spring break? No questions? Nothing? Yes, thank you. Yeah. Okay. Well, that's a great question. So coherent states are actually, how many people have looked at the optional problems? Nice. Okay, good. So coherent states were a topic that we touched on the problem sets and on the optional problems. And the optional problems are mostly on the harmonic oscillator and nice. Nice problems revealing sort of the structure of the harmonic oscillator, and it generalizes quite broadly. But here's the basic idea of coherent states. Let me just talk you through the basic ideas rather than do any calculations. So what's the ground state of a harmonic oscillator? What does its wave function look like? It's a Gaussian, exactly. It's a minimum uncertainty wave packet. How does it evolve in time? Yeah, phase. It's an energetic state. It's the ground state. So it just evolves in time to the phase. So if we look at the wave function for the ground state, why not? It's something like e to the minus x squared over 2a squared. with some normalization coefficient we're going to go worry about. Okay. And so this is a minimum uncertainty wave packet. Its position distribution is time independent because it's a stationary state. And its momentum distribution, which is also Gaussian, the Fourier transform, is time independent. And so this thing, up to its rotation of the overall phase, just sits there and remains a Gaussian. Now, here's the question. Suppose I take my harmonic oscillator potential, and I take my Gaussian, but I displace it a little bit. It's the same ground state, but it's the same state, but I just displaced it over a little. What do you expect to happen? How will this state evolve in time? So we know how to solve that problem. We take this state, it's a known wave function at time zero. We expand it in the basis of energy eigenstates. Each energy eigenstate evolves in time of the phase, so we put it in that phase and redo the sum and recover the time evolution of the full state. And we've done this a number of times on the problem sets. Yeah.
Would the Gaussian, does the Gaussian evolve the same way that it keeps with if it had any other initial width other than the one of the ground state?
Let me come back to that. This is a little more precise question. Okay. So we know how to solve this problem practically, algorithmically. But here's a nice fact. I'm not going to derive any equations. That's part of the point of the optional problems. But here's a nice fact about this state. So it's clearly a minimal uncertainty wave packet because at time zero, because it's just the same Gaussian, just translated over a little bit. So what we'd expect naively from solving is we expand this in Fourier modes and then let the system evolve in time. We let each individual Fourier mode, let each individual energetic state evolve in time, become a phase. And now what we get is a superposition. Instead of sum over n at time zero, we have sum over n Cn phi n of x. Now, as a function of time, we get e to the minus I omega n t. And these phases are going to change the interference for summing up all these energetic states. And so the system will change in time because the way that the various terms in the superposition interfere will change in time. So very naively, what you might expect, if you just took a random function, for example, if I took a harmonic oscillator potential and you put some stupid function that did, something like this, what would you expect it to do over time? Well, due to all the complicated interference effects, you'd expect this to turn into basically some schmutz, just, some crazy interference pattern. The thing that's nice about a coherent state, and this is where it gets its name, is the way that all of these interference effects conspire together to evolve the state is to leave it a Gaussian that does nothing but translates in time. A coherent state is coherent because it remains coherently a Gaussian as it moves along. It oscillates back and forth. And in fact, the peak, the center of this Gaussian wave packet, oscillates with precisely the frequency of the track. It behaves just as a classical particle would have had you displaced it from the center of the harmonic oscillator track. It oscillates back and forth. Now, on the other hand, you know that its momentum is changing in time, right? And at any given point, as you've shown on the problem set that's due tomorrow, or you will have shown, at any given moment in time, the momentum can be understood as the overall phase. You just change that momentum by the overall phase, so it's the spatial rate of changing phase, e to the kx. So you know that the way the phase depends on position is changing over time. So it can't be quite so simple that the wave function, rather than the probability distribution, is remaining a Gaussian over time. It's not. It's got all sorts of complicated phases. But the upshot is that the probability distribution oscillates back and forth perfectly coherently. So that seems a little magical, and there's a nice way to understand how that magic arises, and it's to understand the following. If I take a state phi 0, but I translate it x minus x naught, okay? So we know that the state phi 0 of x was the ground state. What does it mean to be the ground state of the harmonic oscillator? How do I check to find the ground state of the harmonic oscillator? Look, I walk up to you and I'm like, hey, I'm the ground state of the harmonic oscillator. You're suspicious. What do you do? Annihilate. Exactly. You act with the annihilation operator. Curse you. So you act with the annihilation operator and you get 0, right? What happens if I act with the annihilation operator on this? Is this the ground state? No, it's been displaced by x naught, and meanwhile I told you that it oscillates back and forth. So what happens if you act with the annihilation operator? Should you get 0? No, what are you going to get? Some random schmutz, right? If you just take A and you act on some stupid state, you'll just get some other stupid state. Except for Gaussians that have been displaced, you get a constant times the same wave function, phi 0 of x minus x naught. Oh, it turns out that these displaced Gaussians are eigenstates of the annihilation operator. What does that mean? Well, it means they're coherent states. And so the optional problems are working through of the study of the eigenfunctions of the annihilation operator, the coherent states. Is that cool? It's a state, it's a superposition. You can think about it like this. It's a superposition of the energetic states, right? Any state is a superposition of energetic states. The coherent state is just some particularly special superposition of energetic states. So you can think about it literally as C0 phi 0 plus C1 phi 1 plus C2 phi 2 blah blah blah. Right? What does the annihilation operator do? What does the lowering operator do? It takes any state and lowers it with some coefficient. So a coherent state, an eigenstate of the annihilation operator, must be a state such that if you take C0 phi 0 plus C1 phi 1 plus C2 phi 2, you hit it with the annihilation operator, which will give you C1 phi 0 plus C2 phi 1 divided by root 2 plus dot dot dot, or times root 2 divided plus dot dot dot. It gives you the same state back. So that gives you a relation between the coefficients, C0 and C1, C1 and C2, C2 and C3. They've all got to be suitable multiples of each other. And what you can show, and this is something you work through, not quite in this order, on the optional problems, what you can show is that doing so gives you a translated Gaussian. Okay. So physically, that's what a coherent state is. Another way to say what a coherent state is it's as close to a classical object as you're going to get by building a quantum mechanical wave function. It's something that behaves just like a classical particle in that potential would have behaved in the harmonic oscillator. Did that answer your question? Okay. Anything else? So Matt works with you for a living. Matt, do you want to add anything? All right. I like these. They show up all over the place. This is like the spherically powered wave functions. Because awesome. It's an Eigen function. It's an annihilation operator. It's like a classical particle.
Is there an easy way to define coherent states, the potentials where you don't have nice objects? Okay.
Yeah, I mean that's usually what we mean by coherent state. So the term coherent state is often used interchangeably in many different things, which in the case of the harmonic oscillator are identical. One is a state, which is a Gaussian. Okay, so in the harmonic oscillator system, that's a particularly nice state because it oscillates particularly nicely and it maintains its probability distribution as a function of time, roughly by translating possibly some phases. But people often use the phrase coherent state even when they're not harmonic. And it's useful to keep in mind that we're often not harmonic. Nothing is truly harmonic. So, but you had another question a moment ago, though. And your question was about the width. Yeah.
It just translates without changing its width.
Exactly.
Without changing shit at all. If the Gaussian were of a different width, would that still happen?
Yeah, it does. Although the details of how it does so are slightly different. So that's called the squeeze state. And the basic idea of a squeeze state is this. Suppose I have a harmonic oscillator. Okay. And this is actually how people build. Well, this is one way people build squeeze states in labs. So suppose I have a harmonic oscillator, I put a system in ground state. So there's its ground state, and its width is correlated with the frequency of the potential. Right. Now suppose I take this potential at some moment in time, and I control the potential. The potential is like created by some laser field, for example. And some annoying grad student walks over to the control panel and doubles the power of the laser. Right? All of a sudden, I squeeze the potential. Okay? But my system is already in a state which is a Gaussian. It's just the wrong Gaussian. So what does this guy do? Well, this is funny. The true ground state, once we squeeze, right? The true ground state would be something that's much narrower in position space. I didn't draw that very well, but it would be much narrower in position space. And thus, its distribution would be much broader in momentum space. So the state that we put the system in, or we've left the system in, has too much position uncertainty and too little momentum uncertainty. It's been squeezed compared to the normal state in the delta x delta t plane. Its uncertainty relation is still extreme. It still saturates the uncertainty because it's a Gaussian, but it doesn't have the specific delta x and delta t associated with that, with the true ground state, with the squeezed potential. Okay, so now you can ask, what does this guy do in time? And that's one of the optional problems too, and it has many of the nice properties of coherent states. It's periodic. It evolves much like a classical particle, but its uncertainties are different, and they change shape. It's an interesting story. Okay, that's the squeeze state. Yeah.
Do other potentials have coherent states that are Gaussian?
It sort of depends. So other potentials have states that behave classically. Yeah, they're generally so systems that are harmonic oscillator do have very special states that behave like a classical particle, but they're not as simple as annihilations by the annihilation operator. Come to my house, I'll tell you about sort of analogous toys for something called supersymmetric quantum models, where there's a nice story there. Okay, I'm gonna cut off coherent states for the moment and move on to where we are now. Okay, so last time we talked about scattering of a particle, a quantum particle of mass m against a barrier. And we made a classical prediction, which I didn't quite phrase this way. We made a classical prediction that if you took a particle of mass with this particle of mass m and threw it against a barrier of height v0, that the probability that it will transmit across this barrier to infinity is basically 0. So this is the classical prediction. It will not transmit to infinity until the energy goes above the potential. And when the energy is above the potential, it will slow down, but it will transmit 100% of the time. Okay. So this is our classical prediction. And so we sought to solve this problem. We did, which is pretty straightforward. And the energy eigenstate took the form, well, we know how to solve it out here, we know how to solve it out here, because these are just constant potentials, so it's just plane waves. Let's take the case of the energy is less than the potential. So this guy. Then out here, it's in a classically disallowed state, so it's got to be an exponential. If we want it to be normalizable, we need it to be a decaying exponential. Out here, it's oscillatory, because it's a classically allowed region. And so the general form of the wave function of the energy eigenstate is a superposition of a wave moving this way with positive momentum, a wave with negative momentum, a contribution with minus k. And out here, it had to be the decaying exponential. And then by matching, we're requiring that the wave function was oscillatory and then exponentially decaying out here, and requiring that it was continuous and differentially continuous, that its derivative was continuous. We found matching conditions between the various coefficients, and this was the solution in general. Okay? Now, in particular, this term, which corresponds to the component of the wave function moving towards the barrier on the left-hand side, has amplitude 1. This term, which corresponds to a wave on the left with negative momentum, so moving to the left, has amplitude k minus I alpha over k plus I alpha, where h bar squared k squared on km is equal to, that's just the energy, E, and h bar squared alpha squared on this side is equal to v minus E. But this normally is a pure phase, and we understood that, so we'll call this parameter R, because this is the reflected wave, this is an amplitude rather than a probability, so we'll call it R. And you notice that this, the probability that we get out, so we want to ask the question, what is the transition probability that I get from far out here to far out here? What is that probability?
1.
So if I consider a state that starts out as a localized wave packet way out here, and I send it in with energy below barrier, what's the probability that I'll get arbitrarily far out here, that I will subsequently find a particle very far out here? 0, right, exactly. You can see that because here's the probability amplitude, the north squared is probability density as a function of position, and it goes like a constant times e to the minus alpha x for large x, this exponential tildes. And we get that more precise by talking about the current. We said, look, the current that gets transmitted is equal to, that's a funny word, h bar, the current that gets transmitted, which is equal to h bar upon 2mi psi complex conjugate dx psi minus psi dx psi complex conjugate on the right. This is just equal to 0. And the way to see it, the easiest way to see that is something you already showed on the problem set. The current vanishes for it. The current vanishes when the wave function can be made real out to a phase. And since this is some number, but in particular it's an overall constant complex number, and this is a real wave function, we know that this is 0. So the transmitted current out here is 0. The flux of particles moving out to the right is 0. Okay? So nothing gets out to the right. So that was for the energy less than the potential, and we've now re-derived this result, the classical prediction. So the classical prediction worked pretty well. Now, importantly, in general, we also wanted to define the transmission probability a little more carefully, and I'm going to define the transmission probability as the current of transmitted particles on the right divided by the current of transmitted probability that was incident. And similarly, we can define a probability that the particle reflects, which is the ratio of the reflected current, the current of the reflected beam, to the incident current. Okay? And so this is going to be the transmission probability and reflection probability. Yeah? Thank you. Okay. So let's do a slightly different example. In this example, I want to study the same system, the wall.
Why are these squared? Let's see if I can't understand that. Why is that squared? This should be so we know that this is equal to probability over time.
Yeah. Thank you. Okay. So let's do a slightly different example. In this example, I want to study the same system, the wall, but I want to consider a ball incident from the left, an object, a quantum particle incident from the left, with energy greater than V, greater than V naught. So again, classically, what you expect in this case, you send in the particle, it loses a little bit of energy going up the potential barrier, but it's still got a positive kinetic energy, and so it just keeps rolling. It's like my car making it up the driveway. It just barely makes it. Okay, so here again, what's the form of the wave function? Phi e can be put in the form on the left. It's going to be e to the I dx plus e to the minus I dx, and that's over here on the left. And on the right, it's going to be the form c e to the I k. In fact, we call this k1x and k2x, or sorry, k1x, which is on the left. H bar squared k1 squared upon 2m is equal to e. And on the right, we're going to have k2x because it's, again, a classically allowed region. It's going to be oscillatory, but with a different momentum. E to the I k2x plus d e to the minus I k2x. Okay. Where h bar squared k2 squared on 2m is equal to e minus v naught, which is a positive number, so that's good. So here's our wave function. And before we do anything else, I want to just interpret this quickly. Because, this is like a wave that has positive momentum, and I'm going to say that it's like a contribution of term in the superposition that is moving to the right. The right thing that is moving to the right. Well, first, let's see how positive momentum. But more important, this is an energy-eigened state. So how does this state evolve in time? It's an energy-eigened state with energy. How does it evolve in time? It rotates by an overall phase. Exactly. So we just get this times an e to the minus I omega t, where h bar omega is equal to e, the energy. And that term on the left or right, the energy is just a constant. So this term goes as e to the I kx minus I omega t, or kx minus omega t. And this is a point of constant phase in this, move to the right as t increases in order for the phase to be constant, or for this phase, for example, to be 0. As t increases, x must increase. By assumption here, k is a positive number. On the other hand, this guy, that was a k1, the second term is of the form e to the minus I k1x. And when I add the omega t minus I omega t, this becomes kx plus omega t, so point of constant phase, for example, phase equals 0. In order for this to stay 0, then as t increases, x must become negative, x must decrease. So that's why we say this corresponds to a component of the wave function, a term in the superposition, which is moving to the left, and this is one which is moving to the right. Sorry, my right, your left. Sorry, this is moving to your right, and this is moving to your left. Okay? It's a little Z2, it's harder than it seems. Okay, so we can imagine two different kinds of scattering experiments. We can imagine a scattering experiment where we send in a particle from the left, and that's what happens. So if you send in a particle from the left, what are the logical possibilities? It could go through, or reflect back. Are you ever going to get a particle spontaneously coming from infinity out here? Not so much. So if you're sending a particle in from the left, what can you say about these coefficients? D equals 0 and A is not 0. Right? Because D corresponds to a particle on the right-hand side coming in this way. So that's a different scattering experiment. So in particular, coming in from the left means D equals 0 and A not equal to 0. Coming in from the right means A equals 0 and D not equal to 0 by exactly the same token. Cool? Okay, so I want to emphasize this. A and D, when you think of this as a scattering process, A and D are in, guys. In. And C and B are out. This term corresponds to moving away from the barrier. This term corresponds to moving away from the barrier, just on the left or on the right. Okay? Out. And out. Everyone happy with that? Yeah.
A, D.
E is bigger than the out that transfer within one. Doesn't that mean that?
So this is this is the classical prediction. Classical prediction. Yeah. So let me rephrase. The question was basically, what that classical prediction implies that B must be 0 in the other scattering process, and that doesn't sound right. So is that true? No, it's not true. We'll see it again in a second. So very good intuition. That was good. Yeah. Okay. Good. So in general, if we have a general wave function, general superposition of the two states with energy E, with A, B, C, and D all non-zero, that's fine. That just corresponds to sending some stuff in from the right and some stuff in from the left and some stuff in from the right. Yeah? But it's of course going to be easier if we can just do a simpler experiment. If we send in stuff from the left or send in stuff from the right. And if we solve those problems independently, we can then just superpose the results to get the general solution. Yeah? So it will suffice to always either set D to 0 or A to 0, corresponding to sending things in from the left or sending things in from the right. And then we can just take a general superposition to get the general answer. Everyone happy with that? Okay. So let's do that in this setup. So here's our wave function. And you guys are now adept at solving the energy eigenvalue equation. It's just the matching conditions for A, B, C, and D. I'm not going to solve it for you. I'm just going to write down the results. So the results, we'll use a new board. The results for this guy, now for E greater than V, are that, what just happened? Right, okay, good. So let's look at the case D equals 0, corresponding to coming in from the left. So in the case of in from the left, C is equal to 2 K1 over K1 plus K2, and B is equal to K1 minus K2 over K1 plus K2. And this tells us, running through the definition of J, the currents, and T and R, gives us that at the end of the day, the reflection coefficient is equal to K1 minus K2.
I'm going to write this R. And write it R.
Upon K1 plus K2, norm squared. Whereas the transmission amplitude, or probability, is equal to 4K1 K2 over K1 plus K2 squared. Okay, and a good exercise for yourself is to rederive this. You're going to have to do that on the problem set as a warm-up for a problem. Okay, so at this point, we've got an answer, but it's not terribly satisfying because K1 and K2, let's put this in terms of more easily interpretable form. K1 and K2 are nothing other than code for the energy and the energy minus the potential, right? So we must be able to rewrite this purely in terms of the energy and the potential E and V. And in fact, if we go through and divide both top and bottom by K1 squared for both R and T, this has a nice expression in terms of the ratio of the potential to the energy. And the nice expression is 1 minus the square root of 1 minus V naught over E over 1 plus the square root of 1 minus V naught over E norm squared. And similarly, the transmission amplitude has the form 4 root 1 minus V naught over E over 1 plus the square root of 1 minus V naught over E squared. Okay. I don't remember which version of the notes I posted for this year's course. In the version from 2011, there was a typo that had here E over V, and in the version from 2012, that was corrected in the notes to be E over V naught over E. I'll check. But let me just warn you about that on 1 or 2 pages of the notes at some point. These guys were inverted with respect to. So write this out. Now we can plot the following. We can now plot the quantum version of this plot. We can plot the actual quantum transmission as a function of energy. And the classical prediction was that at energy is equal to V naught, we should have a step function. But now you can see that this is not a step function. And that's related to the fact that B was not actually 0. Right? As you pointed out. Hold on one sec. Oh, sorry. Was it quick? Okay, the notes are wrong. Good. Thank you. Oh, that's great. Okay, so the notes are wrong. So it should be V naught over E, not E over V naught on the notes that are posted. We're in the process of teching them up. So eventually this will be available. Extra elbow grease. Okay, so what do we actually see? So here we got for E less than V naught. We got an E that the transmission probability was exactly 0. So that's a result for the quantum result. But when E is equal to V naught, what do we get? Well, when E is equal to V naught, this is 1. We get square root of 1 minus 1, which is square root of 0, over square root of 1 plus square root of 1 minus 1, which is 0. Square root of 1. That's 0 over. Okay, good. So that's not so bad, except for this 1 over this E. This is a little bit worrying. If you actually plot this guy out, it does this. Where it asymptotes to 1. And to see that it asymptotes to 1, just take E naught gigantic. If E naught is gigantic, this becomes V naught over E, which goes to 0. And if E is much larger than the potential, so this becomes square root of 1. And in the denominator, this becomes square root of 1. 1 plus 1, that's 2 squared, 4. 4 divided by 4, that goes to 1. So for large E, much larger than V naught, this goes to 1. So we do recover the classical prediction if we look at energy scales very large compared to the potential height. Yeah? Okay. So that's nice. Another thing that's nice to note is that if you take this reflection probability and this transmission probability, then they sum up to 1. This turns out to be a general fact and a necessary condition in order for those to be interpretable as reflection and transmission probabilities. The probability that it transmits and the probability that it reflects had better add to 1, right, which is probably not what you're looking for. So this turns out to be true in this case just explicitly, but you can also, as you will in your concept, prove that from that definition of R and T, it's always true. a check on the sensibility of our definition. If it weren't true, it wouldn't tell you that quantum mechanics is wrong. It would tell you that we chose a stupid definition of the transmission and reflection probabilities. So in this case, we actually chose quite differently. Okay, questions at this point? Yeah.
Is this now like classical particles? We're talking about like the difference between, like if I threw a baseball and I happened to throw it at a potential that had height, like 1 million of a joule less than the energy of the baseball, would we observe this also?
No, for the following reason. So here's my classical system. Okay, classical system is, literally some hill. Where I was growing up as a kid, there was a hill not far from our house. Well, I'm not even going to go into it, but it was horrible. So if you have energy just ever so slightly greater than the hill, he said from some experience, if you have energy that's ever so slightly greater, okay, I'm going to resist the temptation. One of these days. If you have energy that's ever so slightly greater than the hill, okay, and you start up here, what does that tell you? What does it mean to say you have energy just ever so slightly greater than the potential energy at that point?
You're moving.
Little tiny velocity. Okay, I'm going to say I have little tiny velocity this way. Okay. So what happens? We follow Newton's equations. They are totally unambiguous. And what they tell you is, with 100% certainty, this thing will roll and roll and roll, and all hell will break loose. And then if you're very lucky, your car gets caught in the trees on the side of the cliff, which is later referred to by the policeman who helps you tow it out as nature's guardrail. I was young, it won't happen again. So, with 100% certainty, Newton's equations send you right off the cliff, and for style points, backward. So now I'm going to do the second thing. Newton's laws satisfy time reversal invariance. So the time reversal of this is, this thing has this much energy, and it shoots up the cliff ever so slowly, it just eventually goes up to the top, where everything is fine. Okay, but does it ever reflect back downhill? No. And does it ever, classically, when you roll the thing, does it ever actually not go off the cliff and hit the trees, but instead reflect backwards? I wish the answer were yes. But sadly, the answer is no. Now, if that car had been quantum mechanically small, my insurance would have been much more manageable. But sadly, it wasn't. Okay, so this is a pretty stark and vivid, this is a pretty stark difference between the quantum mechanical prediction and the classical prediction. Ever cool with that? Other questions? Yeah.
I just had my first yeah. I'm not trying to show the division square.
Excellent. Okay, so the reason to do it, so great, excellent. How to say? So when you calculate out, so here's one way to think about it. So the first thing we want is so this is a very question. Let me repeat the question. The question is like, why is it squared? Why isn't it linear? So let's think about that. The reason it's squared is because of a typo. So let's think about let's think. Okay, it's a very good question. So let's think about what it should be. Okay, so let's put an arbitrary power there. And let's think what it should be. Thank you so much for this question. I owe you like a plate of cheese or something. So that's how you praise guys, right? So it should be linear, it should be quadratic. What is that supposed to represent? What is T, the capital T, supposed to represent? Probability of transmission, exactly. The wave function is the wave function at the value of the wave function point. Is that a probability? Is it a probability density? It is a probability amplitude. It is a thing whose norm squared is a probability. So we want something that's quadratic in the wave function, right? Meanwhile, sometime before, we wanted a definition of how much stuff is moving past a point at a given moment in time. Right? What's the probability density moving past a point at a given moment in time? And that's where we got the current J from in the first place. J was the probability density moving past a point at a given moment in time. Really more precisely, well, yes. So notice that J is quadratic in the wave function. So it's how much stuff is moving past in a particular direction. Right? It shows it to be the incidence of the reflected bit. At a moment in time, so the probability density is actually current. And it's quadratic in the wave function. So it has the right units and the right structure to be a probability. If we squared that, we would be in trouble because it wouldn't be a probability, it would be a probability squared. And in particular, it wouldn't normalize correctly. So that typo was actually a bad typo. So what happened, now think back, so you have a video someday, so you can scroll back to what happened was I didn't put the squared on the first, I put the squared on the second, and someone said squared on the first. Yes, but the correct answer is no squared on the second. So there are no squares. Thank you for the question. Very good question. In particular, the thing that was so awesome about that question was it was motivated by physics. Right? It was like, look, why is this thing squared? Like, that's two factors of the wave function already quadratic. It should be like a probability. Very good question. Yeah.
Just as a side note, I had previously spent a couple minutes trying to figure out why that is squared, and it turns out it was a typo. It's part of the reason that I like watching the end of the lectures before stopping.
Yeah, okay, so looking back at that question a little bit, let me just quickly say that we calculated it, and we see explicitly that it's 0. Now you might say, well, look, the true wave function has a little bit of a tail. Right? So, there's some finding probability to find it here if you do a measurement. But the question we want to ask in transmission is, if you send it in from far away over here, how likely are you to catch it far away over here? And the answer is you want to not. That makes sense? Okay, good. Okay, so much for that one. Now, here's a fun fact. I'm not going to go through this in any detail. We could have done exactly the same calculation. Okay, we could have done the same calculation sending something in from the right. Yeah, and sending something in from the right. In on the right corresponds to d not equal to 0, and nothing coming in from the left is a equals 0. We could have done a case a equals 0, which is in from the left, in from the right. Okay, and if you do that calculation, what you find is that c is equal to k1 minus k2 upon k1 plus k2. D and B is equal to 2k1 upon k1 plus k2 d. Okay, and this says that plugging these guys in, the reflection and the transmission are the same. In particular, physically, what does that mean? That means the reflection and transmission are the same uphill as downhill. Well, downhill is uphill. Okay. They're the same both ways. But that's truly weird, right? What's the probability to transmit quantum mechanically if you have just a little bit of energy and you send a particle in? How likely are you to go off the cliff? If we have energy ever so slightly greater than the potential, and the transmission amplitude is the same downhill as it was uphill, how likely are you to fall off the potential? Never. Because if energy is just slightly greater, then the transmission probability is very, very low. Right? The transmission to go from here to here is extremely low if the energy is close to the height of the barrier. So had I only been on a quantum mechanical hill, you would have been just fine. Right? This is a really striking result. This thing, the fact you're unlikely to scatter uphill, that's maybe not so shocking, but you're really unlikely to scatter downhill. That is surprising. Okay. So I leave it to you to check that, in fact, the transmission, when you do it in from the right, the transmission and reflection probabilities are the same. Recalling that transmission means going this way, reflection means bouncing back to the right. Cool? Yeah. Geez, today is a disaster. There's a typo. This should be times A. It should be times A. First off is that these should have the appropriate dimensions. So there should be an appropriate power A. And the second thing is that if you double the stuff in, you better double the stuff out. So if you double A, you better double C. So there better be a factor of A here. And that's just a typo. I'm sorry. Today is a bad day at the chalkboard. Thank you for that question. Yeah.
Is there a physical reason for why RT are the same and so different for what? For what we class-based factors that just really matter?
There is. I want you to ponder that. And either at the end of the day or at the beginning of tomorrow, we'll talk about that in more detail when we've got a little more technology. So it's a good question, and you should have that tingling sensation in your belly that it's something that's confusing, surprising, and requires more explanation. And we'll get there. But I want you to just think about it in the background first. Yeah. Nope. So the question is there any experiment in which R and T don't sum up to 1? And there are two ways to answer that. So the first way to answer that is it turns out that R and T adding up to 1 follows from the definitions. Okay, so one of the things you'll do on the problem set is you'll show that using these definitions of the transmission reflection probabilities, they necessarily add up to 1. Strictly, they have to. They fall from the Schrödinger equation. The second answer is, let's think about what it would mean if R and T didn't add up to 1. If R and T didn't add up to 1, that would say, look, if you throw a particle in at a barrier, at some feature of potential, some wall, then the probability that it goes this way at the end versus the probability that it goes that way at the end if you wait long enough is not 1. So what could have happened? It could have gotten stuck in there. But that doesn't even consider momentum, right? Not even approximately. And we know that the expectation of momentum is time dependent. So for a free particle. So if this guy, in between, well, it's actually the potential is not actually time dependent. The potential is a force, but. Well, here, okay, so if you're talking about multiple particles and interactions amongst multiple particles, it's a slightly more complicated question. The answer there is still, yes, it has to be the total probability in is the total probability out, but we're only going to talk about single particles here. But it's always true that we're going to take this as an assumption, that things don't just disappear. Okay, that the number of particles or the total probability is concerned. And there's a third way to say this. This really isn't independent from the first. Remember that this current, these were defined in terms of the current. The current satisfies the current constant probability conservation equation, dt of rho is equal to the gradient minus the gradient of the current. Okay. So that probability is always conserved. The integral of probability density is always conserved. It's time independent. Yeah, it's by construction, exactly. Okay. Yeah.
So I think I'm going to just pause it right there because that seems like as good as any to pause. We've got about 5 minutes left, and I like to do a little recap before I sign off for the day. So what are we at now? We're kind of halfway through lecture 13. We did 2.5 lectures. I mean, the material's hard, so I think we may have the same challenges, or I might have the same challenges. Can't keep using we when it's me learning this stuff and I have to talk about myself. I might have the same challenges that I had when I was working on it earlier, where you know, I might have to go back and refresh some things. So far, things seem pretty good. I feel like I understand this. I mean, I'm going to have to work through it in the problem sets. But I think I want to stick with the current trajectory right now, which is trying to finish all the lectures by Friday so we can get back, focus on problem sets exclusively. But we'll just see. If it feels like I'm getting real far into things without really understanding it, then we might pause and do that. The challenge is, as I said, it's hard to have that time management on the problem sets if you don't know what's going to be easy and hard later on. So that's the reason I like to do it like this. Yeah, I think overall I'm feeling okay about this. So I'm going to just leave it for right now and join back in at tomorrow morning. Try to do the same thing. I think probably Wednesday, Thursday, Friday is going to be all lecture days. So it's just going to be working on that. I may take a pause to work on things. You can kind of see how I'm working on things. I'm going through the lecture, but I'm pausing to write things down or to ask questions. Sometimes it turns out those questions are because there's a typo. And so I'm writing down and like trying to figure out why the heck this is a square term. And it's because it doesn't have a square term. So that's at least a kind of satisfying thing when you're spotting those errors, or you're noticing there's a confusion because that's actually not right. So it's a good check on that you understand it. Of course, there's a lot of work to be done. Still working on the problem, so still working on these things. So see how far I can go. It was about, I think we started this lecture. Yeah, we started lectures this afternoon. It's been 3 hours. We've done 2.5. So, I mean, we're a little bit like, it's like 1.25 times the speed. So I think at that rate, you know, if we're doing 2.5 lectures per study chunk, that means 5 per day. Yeah, I think we could probably finish everything by Friday if we're able to sustain this pace. If I'm able to keep going like this. Yeah, so I think this is going fairly well. We'll just sort of have to see, I guess, when we get into the problem sets at the end of the week, what it actually looks like and what I have to learn and what I have to work on. I've already got my sheet. I've crossed some things off here, but there's still quite a bit on it that I'd like to do deeper work on. And then obviously lots of problem sets, lots of problems to do, not only the problem sets that are given in this class, but I got a textbook with some problems, and I might be able to dig up some that have solutions from other sessions of the class. So thanks for following. I will be back online tomorrow morning.